So hello everyone, welcome to this workshop on interactive robot learning. So it's a pleasure to have people now connected from all around the world. Unfortunately, we cannot be together in Paris this year, but on the other hand, we can allow to join more people that wouldn't be anyway in Paris. So we have decided to do this workshop in this hybrid way of synchronous and asynchronous presentations and discussions in order to have also flexibility for all the time zones that are in all the world. So it is not a problem for everyone to be like 10 hours connected to a traditional workshop that is being held online. So we decided to do this synchronous part of the discussion, which is like maybe the most relevant, which we could make questions, ask questions to the speakers and the authors of the contributions, and also to like discuss general questions or problems or challenges that we have in this topic. So first I would like to introduce the organizers. So Carlos Solmin, I am Carlos Solmin, Haris Ravichandar, Raul Imperio, Jens Kober, Maya Kalmat, Sonia Shonova, and Sylvain Collinon. So this workshop is about interactive robot learning, but first, like to be in the context, we have machine learning methods for solving problems of the sequential decision-making problems. So basically, we have two branches: the autonomous learning one and the intentional learning one. In the autonomous learning is basically mostly covered by reinforcement learning, in which an agent is interacting with environment, and by trial and error is getting experience and figuring out how to behave in order to achieve a goal or a task. On the other hand, we have intentional learning, in which an agent is receiving the knowledge of another agent, or it could be a person. So this is more about transferring some knowledge from another agent. Both these possibilities have advantages and disadvantages. We have, in this case, focus on intentional learning. So we have also branches in intentional learning that could be the sequential methods that are mostly the traditional ones, in which basically there are demonstrations or any recording of a different kind of feedback that are taken, and then we apply algorithms to obtain policies afterwards, after we have a batch of demonstrations or any kind of feedback that the user will give to some executions of task. On the other hand, we have interactive intentional learning, in which the user is involved in the learning loop of the learning process. So this knowledge is not transferred in the initial step, but it is being transferred throughout the whole learning process. So basically, the user is observing the interaction of the agent and environment, and is providing a sort of feedback that could be many possibilities, like it could be evaluative feedback, it could be corrections, demonstrations or corrective demonstrations, preferences, rankings, etc. So there are lots of different methods in interactive intentional learning that are classified depending on the kind of feedback that is given or the kind of interface that the user is using for transferring or communicating to the robot the feedback. Also, the methods are classified depending on what is learned from this interaction. If it is learned, for instance, an objective function or to-be function, or if it is a policy that is being learned. And these methods could be also online or offline. And I think like we have also a classification based on model free or model based, depending on what knowledge we have about the environment. So based on all these introductions, we have invited some very well-known researchers to present and talk about what they have discovered in this field. But also we have some contributions of authors that are presenting some preliminary results of their work. So basically, we are splitting these discussions first in 1 hour, in which we are inviting the authors of the contributions to to be present, and we will ask some questions that we already collected from other participants of the workshop previously, and we will have 5 minutes for each of you. So we will invite the person, the first author, to introduce him or herself quickly, like with one sentence basically, and then we will start asking the questions. And later on we will proceed to follow with the invited speakers, and we will have a similar session in which we may ask some questions, and then we will also to each of the speakers, but also we will ask some general questions that we would like to discuss with all of you. So we will ask the authors of the contributions to enable their video and their microphone for the moment that we will be asking the questions. So let me stop this. We will invite the first author. Is Andrea Bobu from UC Berkeley. So she's presenting this work, Less is More, Rethinking Probabilistic Models of Human Behavior, which is a already published paper.
Hello.
Hello, Andrea. So we will do maybe like a couple of questions, and then later we'll see if we have more time. So the first question that we have for you is, it was asked by Anis Najar. So it says, does this formula only apply to the continuous domain, or does it also apply to the discrete case? What happens if we use it in a discrete domain where all alternative choices are different? It means like similarity equals 0.
Yes, this formula applies to the discrete domain as well. And if you have a domain and a set of similarity features according to which similarity equals 0 for absolutely every combination of your choices, then this formula should just reduce to the regular Boltzmann model, because yes, it should reduce to the regular Boltzmann model, because then the denominator in our formula basically becomes a similarity score of your trajectory, or sorry, your choice and all the other choices. All the other choices have similarity 0, but your choice and your choice with itself will still have a similarity that is equal to 1 or something. So then that means that your denominator is always 1, which means that the denominator doesn't matter, which means that the formula would just reduce to the regular Boltzmann model. But obviously, this does depend on your environment, or like your specific case actually having absolutely no similarity between any choices.
Okay, thanks. So next question is given also by another author, Niels Wild. In practice, the solution relies on a finite set of samples from the trajectory space. Wouldn't it be possible to duplicate two similar trajectories from that sample set and then use a discrete probability model based on these samples?
Yeah, so you can certainly do that, but that would mean that you have to choose your set such that the similarity between any pair of trajectories is practically null, which seems difficult to do. Or like, to me, it seems like you have to like very carefully hand pick, or not hand pick, but basically just like pick the trajectories that such that the similarity is non-existent. And then another problem with this would be the fact that your observation itself might not, like your observed trajectory might not care about the fact that you just picked this set of trajectories. And the observation still has to belong, like you still have to append it to the set of trajectories. So you would have to make sure that whatever trajectory you observe still has similarity 0 with everything else in your picked set of trajectories. So I feel like that's quite, I mean, you could do it, but I don't think it's quite the right solution in this case. Does that answer your question?
So Niels is here.
Mostly yes. So thanks a lot for this detailed answer. I'm just wondering if you could discuss another time maybe.
Yeah. So the thing is, we have like more than 2 questions for you. So I will ask all the authors, please.
Okay.
The next questions, like you could also answer them in the document later after this workshop is finished. So everyone is happy with the fulfilling the answers. So next author is Anis Nayar, presenting the work Interactively Shaping Robot Behavior with Unlabeled Human Instructions, which is also already published paper. So first question is, will this work extend to allowing different modalities of feedback, speech signals, keyboards, input, etc.?
Yeah, so here in this work, we choose to use gestures as the modality for providing instructions and feedback, but we could also use other modalities like keyboard or speech. Regarding instructions, for example, if we use keyboard, the robot would have to learn the mapping between the pressed keys and their corresponding intended actions. We can also use keyboard for providing also evaluative feedback. But here, for evaluative feedback, we assume that the binary encoding of positive and negative feedback is already given to the robot. We can also use speech, but in this specific implementation of our framework, we need to have a discrete space of speech commands that the robot is able to detect. And for now, we don't deal with complex grammar and complex speech. So this could be a direction for future work.
Okay, thanks. So next question is actually mine. So in the task model you presented, does the evaluative feedback update the policy by in the same way as it is used the temporal difference error for the value function update?
Yeah, evaluative feedback updates the policy in the same way as the temporal difference error from the reward function. And indeed, they can be in contradiction with each other. For example, in states where there are multiple alternatives, multiple optimal actions, the teacher might indicate an action that is different from the one that is promoted by the reward function that towards which the robot is converging. Of course, when the teacher is absent, the reward function will push towards its own direction. But over the long run, as the learning process converges, the temporal difference signal becomes smaller and smaller. So there is at some point, the teacher will be able to correct any action using evaluative feedback. And this correction and these corrections will not be overridden by the reward function. So at the end, the teacher has the total control over the reward function.
But if the teacher, this effect of these corrections or these evaluations is not memorized somehow, there is not a problem of forgetting this?
So we don't build a model of the evaluative feedback. So the signals that are provided are not memorized, but they are integrated into the policy. So the probability of selecting an action will be changed according to which feedback you have. But if you assume, for example, if you receive some feedback at the beginning, and then the teacher is absent for a long time, then the effect of feedback may be overridden by the reward function. So, but if the teacher comes again and provides feedback, he can modify the robot's behavior at its point. So the effect is directly encoded into the policy.
Okay, thanks, Anis. So I will go to the next one. Is Alice Hato. She presented this work, 3D neurosurgical simulator for training robotic steerable catheter agents using generative adversarial imitation learning. So is Alice here? Alice isn't here. She registered, but okay, then we will have to move on. So the next is Divya.
Hello.
Hello. So Harish will ask these questions, right?
Yep. Thanks, Carlos. Hi, Divya. So I was wondering if you could take a couple of sentences to briefly introduce your work, and then we have several questions we can go over.
Sure. Hi, everyone. My name is Divya. I'm a PhD student at Georgia Tech. The work we did in this paper involved trying to figure out how the effect of interaction design changes or affects the human teacher's experience based on the observability of the domain that the teacher is training the agent in.
All right, thanks. So the first question we have here is, do you think it is feasible to also use this method to study how the feedback interface or the feedback strategy affect the user experience?
Yeah, so definitely the feedback strategy. The author that did the study for study 0, which was in a fully observable domain, she actually did do a study testing the feedback strategy, how corrective advice versus directive advice affected the user's experience. So that's definitely something I recommend people to check out. There's definitely scope here to study how the feedback interface affects the user's experience, because we are finding that we use a different feedback interface for the fully observable domain and the partially observable domains. And some of our surprising findings we do think is due to the feedback interface.
Okay, thank you. The next question is about whether you pre-trained the agents or the agents were trained from scratch.
The agents were trained from scratch.
All right. How do you interpret that the subject's frustration is lower in partially observable domain? It seems counterintuitive. Could you provide some thoughts on why do you think that you see those results?
Yeah, so this is one of those surprising findings that we think is due to the feedback interface that was used. In the fully observable domain, teachers were training agents using verbal instruction, and during the partially observable domains, teachers were training the agents using keyboard advice. So we believe that teachers that had to use verbal instruction probably had a bit more frustration with the agents versus teachers who were able to just click keyboards and have their agent move.
Okay. Another question along similar lines that if you could provide intuition for is, why is one step perceived more intelligent with penalties, while the 5-step method is the most intelligent with penalties?
So the one-step agent was perceived more intelligent in domains without penalties, and the 5-step was most intelligent in the domain with penalties. Mm-hmm. And this was one of those things where individually, after we asked the teacher to provide feedback after training each agent, in the partially observable domains, it seemed that after immediately seeing the one-step agent, they liked it the most. They thought it was the most intelligent. However, after seeing all 4, they evaluated that in the end, they preferred the 5-step agent. And we think this comes down to the transparency within the agent. So teachers were able to clearly see what the 5-step agent was doing. And we think because of that, they preferred that in domains with penalties.
All right, thank you. So I think in the interest of time, we will move on to the next speaker. And if we have some time, we will allocate a 5-minute break at the end.
So I guess the next paper is paper number 5. The title is Learning Interactively to Resolve Ambiguity. The main author is Giovanni Francese, so maybe you could say a few words about your work.
Yes, nice to everyone. I am Giovanni Francese. I'm a PhD student in the Department of Cognitive Robotics. I did this work in collaboration with Carlos Levin and Jens Kuber. We try to investigate a main problem that there is in learning from demonstration, is the existence of the ambiguities that can arise when there are few demonstrations. And it's not easy to generalize in situations that are different from the demonstration. In particular, we focused our work in one particular type of ambiguity. This is the selection of the reference frame. When there are a lot of reference frame that can be detected, for example, from a camera, and there is one demonstration, and this demonstration is segmented in different parts. We want to understand in each one of the segments which is the correct frame to refer our trajectory, and then we try to understand how to make this robot aware of these ambiguities with some metrics, and how then, in case of the presence of ambiguities, call again the attention of the human and solve these ambiguities in an interactive way that gives the name to the algorithm, that is LIRA, stands for Learning Interactively to Resolve Ambiguity.
Okay, so there are two questions for your paper, which are actually for myself. So I think it's an interesting work. And but the first question that I have is related to something that I think was not very clear in your presentation. And it's about the policy representation that you used to learn the motion of the robot, right? So can you elaborate a bit on that? So what techniques you're using for this?
Yes, actually, because we are working with a list of candidates, I'm listing all the candidates that are the available candidates, as also there's the structure of the algorithm in the presentation. So all the frames that are available that are detected, for example, from the perception systems are going inside, and then we are filtering this system like through some priors. And I give the example, for example, of using the idea of manipulated frame. So to transfer knowledge from the different segmentations, say if in one of the segments there is one frame that is manipulated, so it's moving accordingly of the position of the end effector, we want to use that information to prioritize that frame. So basically, the way in which I'm representing my policy is to rank all the different frames, giving advantage. So put in order the one that are more likely to be the one corrected. And when I'm giving the feedback, and then also I will directly answer to the second question, that is how I can give feedback. We developed different ways. One was through an interface. So simply the robot was calling through a desktop the attention of the human and was simply saying the choice that you're going to take is wrong or correct. Or through the robot was going towards the goal and the human was touching the robot saying you are going to the wrong direction. And then we developed two strategies. One was simply, okay, you are touching the robot. It means that this is a no, you are going to wrong to two directions. So you're going directly to the next candidate, or you are using also the information of the direction of the feedback, removing all the candidates that are on the other side of the feedback. And simply we are removing these candidates from the list and going to the more likely that is the next one in the list of candidates.
So actually, that was one interesting example that you used in your illustrative examples during the introduction, which was about like discriminating between different objects of different colors and this kind of problems. Is this something that you can easily handle using this approach?
This approach is I'm still trying to make it more general. Also, for example, to the other example of the two different control methods like force control or position control. It's supposed to be as much general as possible, but is mainly in the moment is working in the framework of reference frame selection. The idea of different candidates, so as features like in the colors, is something that you can generalize using the same approach.
Okay, I see. How are we time-wise? I think we're already at the 5-minute mark, right?
Okay.
So maybe we'll move on to paper number 6, interactive learning of temporal features for control, shaping policies and representations from human feedback. And it's a published paper, which I suppose in a Robotics Automation magazine, if I understood correctly.
Yes.
So the first author is Rodrigo Perez Datari. So if you could say a little bit about your work.
So hello, everyone. I'm also a PhD student at TU Delft in the Department of Cognitive Robotics. In this work, this work comes from the motivation that we want to learn from humans to solve different tasks, and also using high-dimensional inputs to policies. So, for example, raw pixels from an image. That's the motivation, because we think that this enables humans to teach robots or customize robots for different tasks, for example, in household environments. But the problem with this is that deep learning algorithms, because we're using neural networks, take time to learn. They may be like really hungry in a data perspective. So we want to make them learn quickly, because otherwise we cannot use them. So that's why we mix interactive learning, interactive imitation learning with state representation learning, in order to make this learning feasible in a period of time that a human can use to actually teach policies. That's the motivation of the paper.
Okay, thanks for the intro. So there's one long question that I split into two, and there's another one, a third one. So I'll start with the question from Anis Najat, which is, can you say a word about the interaction protocol and how feedback is provided, dynamics, interface, etc.? Is it provided simultaneously to task execution, or is it based on turn taking?
Yeah, so the framework that we present is not limited to the type of feedback that you could use, but the experiments that we did were using discrete feedback. So in this case, we used a keyboard and the arrows of the keyboard to show the agent what we want the agent to do. So for example, we did an experiment with a robot arm, and we were telling the robot, here you should move to the left or to the right. And what was the other question, sorry?
Well, if it is provided simultaneously to task execution, or if it's based on turn taking?
Yeah, also in this case, everything actually is simultaneous. So we run this algorithm while the agent is in the environment. We are collecting data from the environment to learn the state representation part of the network. And also we're using the feedback of the human to both kind of guide where to explore, the agent where to explore, and also to shape the policy of the agent, and everything is done online.
So, but for example, in your experiment you had an experiment about orange picking, right?
Yeah.
How did you provide the feedback there? I'm curious about that. Was it also with the keyboard? Because you wanted to discriminate between the good ones and the bad ones, right?
Yeah, so first, so we also used a keyboard, but in that case, that's a kind of an exception, because first we trained the policy to select the oranges. So some oranges were going through this conveyor belt, and we were telling the arm, basically move to the right or to the left in order to get to the orange. And then they were training that policy first. And once that was working, we introduced these pairs that we called, because at the end we were not using real fruits, but that's what they were representing. And then we were training this other dimension of the action after the policy was already able to select the oranges. So first it was moving from one side to the other to select the orange, and then we were inserting some pairs, and we were telling the arm to move upwards when pairs were going towards the arm. So that's how we trained it in that case.
Okay. So the second question is, what is interface used for providing feedback? I think you already replied to this one.
Mm-hmm.
In your experiments, are the teachers present during the entire training period? That's the last one.
Yeah. Also, that's the reason why we want these training periods to be as short as possible, because if they are too long, then it's not feasible for a human to be, 6 hours providing feedback. Mm-hmm. So the case of the arm was you could say the most extreme one, because it took us almost an hour in that case to teach the whole system like a good policy. But that was the worst case. For example, we also trained this with an inverted pendulum, a real inverted pendulum. And in that case, in more or less 10 minutes, a policy was already working. So also depending on the complexity of the problem, if it makes sense to use this or not. But that's more or less the idea.
Okay, thanks for your answers. We are at the 5-minute mark already, so maybe we can move on to number 7.
Mm-hmm. Thank you.
Thank you, Joel.
Thank you.
So next up we have Nils, and could you take a couple of sentences to explain your paper, and then we will get into the questions?
Yeah, sure. So in our paper, we look at how we can improve user specifications. So if you have an autonomous robot, you might want to define some rules like a road network and some areas where the robot should not go in the environment. But the problem is that users are often quite inefficient when they do that. So they set up these rules, and then when they see like the resulting behavior of the robot, they are somewhat disappointed because the robot is much more inefficient than it should be. So they're basically over-constraining these rules. The idea is that some of these rules might be neglected, so you can ignore them, or you can ignore them under some circumstances, and that is that you can save sufficient time by violating them. So there's a trade-off. For every rule, it might be violated for sufficient time benefit. That might be infinite if that rule is never to be violated, but might be less. And instead of asking users to define this trade-off, asking them like, how important is this on a scale of 0 to 10, you rather want to learn this importance of these defined rules. And we do that with active preference learning. So we show the user, here's like the path that a robot would take if it follows all your rules. And here's an alternative where we violate some rules, but we save like 20 seconds by doing that. Which one do you like better? And if they like the one with the violation, then we learn something about the constraints, and we learn, yeah, we're allowed to violate this constraint if you're 20 seconds faster. So that's the basic idea.
All right, thank you so much. So one of the questions we have here is, what happens if the user changes their mind over the training process? So pretty much resulting in a contradiction between what happened before and now. How do you think that will affect the feasibility sets in your work?
That's a very good question. So in this work here, we used a very simple user model. So if the user likes one path better than the other, this describes an inequality about the weights that we have on the constraints. And we just assume that this inequality always holds. So there's no probability with it. So the learning is deterministic. And to answer that question, in short, if you just have one task, you cannot get a contradiction because we always present two new paths that are from that feasible set. So the options that we present are both feasible, so they can't give a feedback that contradicts the previous feedback. However, there are some corner cases that you can get into with multiple tasks. So yeah, you can probably get like contradictions, and that's already answering the third question, like that there's no way of getting back. There's no way of like revising an answer that you got, not with this model. We have some follow-up work where we introduce a probabilistic model to accommodate for that. But of course, there's this trade-off. With a probabilistic model, your learning becomes slower. So you might not improve your specification as much with the same number of iterations. And in the paper that I presented here, we were able to show that with just 20 iterations, we get like a substantial improvement. So that's like the benefit of the simple model. We improve with even fewer iterations.
Okay, thank you. And a related question is about, what are your thoughts on being able to learn multi-strategy preferences? So if there are multiple modes of preferences, do you think that can be directly incorporated into this work?
You mean if you have like multiple users, basically, like one has some preference A, another one has a preference B? Is that the question?
So maybe even a single user. So immaterial of how many users you have. Let's just say there are equally good preferences, two ways to do things. How do you think you will go with that? Do you think there is a direct way to incorporate that into the feasibility sets? Or do you think you would need the probabilistic extension for that?
You need a probabilistic set for that. You kind of have to weaken this feasible set idea. You still have that feasible set, but it's then kind of describing the shape of a density function.
Right.
It's not like half spaces anymore, but it's like kind of like a Boltzmann model. You have like plateaus in a density function. But with that, you could kind of accommodate for like user changes his mind. You just need more iterations to then kind of update your belief towards this like new idea. If you have two different preferences that kind of fundamentally contradict each other, like one user is like, yeah, this rule doesn't matter, and the other one is, this rule matters a lot, then of course you can't accommodate for that. You can only kind of take your best guess right now, and that guess will change if the user changes.
All right, thank you. Another question we have here is, can you speak a little bit about the user interface used for providing and communicating these sort of preferences, and why you would have made that choice as opposed to other interfaces?
So the user interface is basically just showing you a map of the robot's environment, like a 2D environment. And in the first stage, you draw your constraints on that. So you draw roads, you draw boxes that describe areas where the robot should not go or where the robot should go slowly. And that's the first step. Then you submit it to the robot, and the robot then shows you like 2 possible paths it could take on that same map with these constraints on the map. So it kind of shows you can go here, you can go there, shows you some other information. Path A takes so and so long, path B takes a bit less. And then the user can toggle between those paths and exhibit them and then submit that. So that's what the interface is for. And there's actually a good practical reason for using an interface. So if you imagine you have a warehouse and the user sets up these rules and the robot doesn't know which of these rules might be violated and which might be not, there's a chance that there's some rule that's very important for safety reasons. So you kind of want to show this potential robot behavior on an interface instead of demonstrating it in real world. So there's a benefit of this purely interface approach.
Okay, thank you very much.
Thanks.
If there are more questions, of course, we can take stuff offline and you can comment on the Google Doc directly. So next up, we have Gil Wu from UW.
Hi.
Hi, could you take a minute or so to describe your work, please?
Sure. Hi everyone. I'm a PhD student from University of Washington. I work with Sister Universa at this personal robotics lab. So the work is on Bayesian reinforcement learning, which can be used for problems with model uncertainty or multitask problems where the agent needs to identify the task as well. So for example, it could be a maze navigation with multiple possible goal locations or using various tools to do different tasks. And basically, we're trying to solve the problem of scalability and by leveraging on heuristic experts. And we learn to correct these expert suggestions, and we prove that the algorithm makes monotonic improvements from the ensemble of experts and that it learns much faster than typical RL agents. And we believe that we can incorporate this interactive learning as part of the BRPO algorithm. And in that setting, we can probably have very few human inputs because we can rely on these embeddings of ensembles and beliefs when we ask for additional human interactions.
Okay, thank you. So the first question we have here is, what are your thoughts on what would happen if the expert blocks are being replaced by human teachers? And specifically, could you speak to the fact that you could experience suboptimality or noisy information from such experts?
Right. So the experts in our algorithm can be general and it could be human experts. It's just that since we expect to query the experts online, it would have to be copied over into through behavior cloning or invitational learning. But regardless, the humans are, we can handle suboptimal experts for sure because we're learning in a corrective manner. So the RL algorithm would make up for that correction. But there is a little bit of interesting question of noisy and inconsistent human inputs. So for that, I think we have to be a little bit creative in how we design these ensembles. The ensemble itself can be very flexible. For example, you can imagine a setting where all the features or input features are exactly the same, but the human inputs are bimodal. So if you just average them together, you just get zero output. Instead, you can make an ensemble that basically chooses which expert to follow with equal probability. The algorithm can handle stochastic ensembles. So as long as the stochastic distribution itself remains the same during training and testing, you can still incorporate these noisy experts or inconsistent experts into the algorithm.
Okay, thank you. Thanks for that explanation. It actually subsumes another question that I had. So the other question here is, what if you don't have access to a prior set of potential goals? For example, you deploy the robot in a new environment that you've not seen before, so it can't know yet what the potential goals are. Could you leverage some of the skills that you've learned from before?
Right. Yes, I think you're considering a setting where there's a navigation task and you're deployed. You've already trained the robot with some priors, but the testing domain is somewhat different, so you're seeing a different prior there. But the good thing about BRPO or anything that is that because it incorporates beliefs though it depends on the way how you incorporated those beliefs. For example, so if there is some features that can be mapped, if there are any similarities between these previous goals or previous environments and the new environments, even if they're somewhat different, the RL agent can still leverage the previous experiences and even the same set of experts, and it'll take the same corrective actions and realize that it's somewhat different, and it'll have to it'll be able to tell that it's somewhat different because it sees that difference through the representation of belief. So the belief will give you, I'm still very uncertain, so I'll have to do something a little bit more explorative.
Okay, thank you. All right, so let's move on to the next, Joel.
Okay, so the next paper is towards a semantic knowledge-based framework for interactive learning, and the corresponding author is Sharat Akkaladevi.
Hi everyone, I'm Sharat Chandra Akkaladevi from Profactor in Austria, and our work is mainly to teach a very complex task in terms of assembly to a robot using with the help of user interaction. The main goal is we have different kind of learning paradigms. We have learning from demonstration, learning from learning by programming, or learning by interaction. We wanted to see if we can combine these different programming paradigms to a hybrid learning framework where can a user easily teach a complex task to the robot. So what we did was to combine learning by demonstration, where a human physically demonstrates a task, and we only abstract the high-level semantics. And then we exploit the learning by programming paradigm, where we use task frame formalism, where we break down these high-level semantics into manageable robot skills. And then with the help of user interaction, we parameterize these robot skills and then combine everything into one learning framework, and then help the robot in manipulating the objects and also completing the assembly process. So that's basically an abstract.
Okay, thanks for the introduction. So we have two questions essentially for your paper, both from Jens Kober. And actually the first question is a question that I had myself when I read your paper for the first time. So the question is, how does the low-level control / the motion generation work? In the video, this seemed to be a simple point-to-point movement, even without proper grasping. More concretely, how would more complex skills be handled, for example, requiring hybrid position force control?
Okay, so as I said, so first of all, we have learning from demonstration, where a human physically demonstrates a task. So if you are lifting an object and placing it into some location, we capture which object the user has acted on, to which position it has been moved, and what is the consequence of this. So how was object positioned with respect to another object, and aspects like that. And we define them as events. So each event has an actor, a target, and a consequence. We model this from a user perspective. So we store it in the knowledge base. And similarly, as I said, we also have this task frame formalism, where a particular task is broken down into robotic skills. For example, we are assuming that the robot knows how to move from point A to point B, and we are also assuming how the robot can grasp an object. And if you want to pick an object from point A to point B, you simply say, okay, the robot has to go to point A, then go down in a particular orientation, grasp that object, and then go to point B, for example. So these are the set of robot skills. So when the user performs a demonstration, and then we capture this high-level semantics, we find a mapping to a set of robot skills with a similar consequence.
So for example, in that case, yeah. So my question is so in that case, in principle, it's easy to incorporate other features like forces and contacts, etc. Right?
If you're able to model them as this task frame formalism aspect. So yeah, I would say so. Okay. I'm not. So the focus is not on developing these new strategies for this complex robot skills in manipulating objects, but finding a set of known robot skills that can map to the similar consequence as a human, what he has demonstrated.
Okay. So another question is, how would you include error detection and recovery in this framework? For example, if one leg is put in slightly crooked, and falls over?
So, for example, from human demonstration, we assume that the teacher is the one with the complete knowledge, and whatever the teacher shows, the robot has to replicate. So there is no concept of errors when a human is demonstrating something. So we assume that the human is demonstrating everything in a proper fashion. There could be errors when the robot is trying to replicate the same behavior, and then it tries to say, okay, I have to pick an object now, and then I have to place it in a particular location. And now it could be that the gripper slips or it is not able to insert it properly. So what we could also do is we can have external sensing devices or the robot proprioception to figure out if the task was successful or not. One way is to retry the same task if some failure happens, or also the framework could also allow to call back to the user saying that, hey, I've done what I thought was the right behavior, but somehow I failed. Could you help me to recover from this? And it could also potentially suggest some alternative solutions to the user, saying that should I retry, or should I choose another object, or if the object is missing from the scene, for example, it could also communicate this information to the user saying that the relevant object is missing and I cannot proceed with the task, for example. So that could be a strategy.
Okay, thanks for feedback. So I guess it's time to move on to the next paper. So paper number 10. The title is Online Learning of Hybrid Models for Variable Impedance Control of a Changing Contact Manipulation Task. And the first author is Saif Siddiq. Hello, Saif.
Hi. Yeah, can you hear me?
Yes.
Yeah. My name is Saif, and I'm a PhD student at the University of Birmingham. And this work is our first step towards trying to build a framework that can deal with changing contact manipulation tasks. So essentially, we have a robot that's trying to perform a manipulation task in which there is changing contacts happening. That could be because of making and breaking of contacts, or because the robot is performing a task and suddenly the surfaces change or the type of interaction changes. So in this work, we have a framework that tries to leverage the structure involved in the task. So the idea is that all of these manipulation tasks are essentially piecewise continuous. So the dynamics for for the task is piecewise continuous because the dynamics is continuous when the robot is in a particular type of contact, and when it tries to make or break that contact, then it goes into a different discrete dynamics mode. So here we have a framework that learns online to model these discrete dynamics models by learning separate models for each of these discrete contact modes.
Okay, thanks for the intro. So for this paper, we have quite a few, we have 5 questions in total. I'll try to give one to ask one per author. So the first question is from Jens Kober. So this is now based on a clustering approach. An alternative would be some form of regression, for example, to the dynamics parameters. What are the pros and cons?
Yes, so that's a very interesting point, because at present what we are doing is we have a clustering method. So when the robot observes some measurement, it tries to cluster it and finds the closest cluster it belongs to and chooses that appropriate, the model that it learned for that cluster. But the problem here is then that if it keeps seeing new modes, then it has to keep building its own cluster all over again. So the scalability is an issue here. So it might have to build different cluster each time it sees a new mode. But the alternative, as Jens suggested, is having some kind of regression methods. But the problem then is that we will be trying to interpolate between these different modes of dynamics, and directly interpolating between these modes may not be the desired behavior, because the dynamics in this mode that is in between them may not be the same. So it might not be directly interpolable from one or the other of the mode. And also in a particular task, we the number of modes involved in that particular task might be limited. So it may be feasible to keep building clusters for it, but yeah, it's a trade-off. So it's something that, depends on the task, and it's definitely something that I want to look into as well because of this scalability issue. Yeah.
Okay, thanks. So another question, this one's for myself, is how does your approach generalize to other kinds of tasks with varying dynamics? For example, when you pour a liquid, for example. So it's not necessarily contact.
So this is something that we did previously with a colleague of mine, and in there we use the same framework but without these discretely changing modes. So it's essentially, this is going to be a single mode where the dynamics is continuously changing. So our framework, as long as this change in dynamics is continuous, it should be able to adapt. So we tried with different tasks such as pulling springs or trying to move in an environment where the viscosity keeps changing, and it's able to adapt as long as it's continuous.
Okay, I see. So I think there's only time for one more question, and I'll ask you to try to be succinct. So the question is, the problem that you are highlighting in this paper is the clear consequence of the use of a force controller. Do you think that using an impedance controller with variable attractor and stiffness would not obtain successful results of the force controller, but without the problem of the overshooting on the chance of the contact friction? This is from Giovanni Francis.
Yeah, so
did you get the
question? So yeah, I understand. So the problem here is, even if you have a point attractor, it would still mean knowing when to change the attractor or even the stiffness of that impedance controller there. And essentially, the task we consider here has a desired force as well. So the robot has to maintain that force as it tries to move through the task. So in that case, we would essentially we will need this type of force control at least along the axis where it falls.
Okay. So that closes the questions for papers. I think we are on the 5-minute mark, and it takes us to the last paper.
So yeah, next paper, we have Juan Gamboa for the work Interactive Learning for Robotic Visual Experts in Marine Environments. So this is one here.
Yep, I'm here.
So can you introduce your work, please?
Yeah, so in this paper, we're showing a couple methods that we use for creating controllers for our underwater robot that we want to use for collecting scientific data in underwater marine environments. And these two methods, the way we thought fell into the interactive learning world is that the robots, we need to provide them some data that modifies their behavior as users. And we have to do this in a sort of loop where we deploy the robot acts in some way, and then afterwards, because of the limitations of communication and that we have with the robot, we have to take out the robot, process the data ourselves, and repeat in subsequent deployments. So one of these pieces of the work was on doing this sort of offline interaction loop for learning navigation policies for underwater robots, and the other was for learning to where to attend during navigation.
Okay, so you have a question from Jens Kuber. So how do you avoid that the robot damages the coral? The corrections seem to happen offline after this execution of the policy. So actually, I think it happens because you are based on a Dagger scheme, right? So basically, specifically, Jens is asking, do you see any way of combining low-level emergency obstacle avoidance with the interactive policy behavior learning?
So yeah, so I guess we're slowly building up on the capabilities of the robot. So in this first version, what we did was at seat of order, we didn't just deploy the robot autonomously. There was a diver that went with the robot collecting data, and then that data was labeled after the fact, saying like, for this sequence of frames, where should the robot move to? That's the sort of labelings that we gave. And then after every deployment, there was a safety diver right behind the robot, trying to make sure that it doesn't crash. And we had an interface for stopping the robot. That's like the sort of interface that we have at the moment. We can tell the robot stop, but for giving other sort of interaction underwater, it's a bit more complicated. We have colleagues that are working on gesture-based interaction, but it's a bit tricky when you're managing like keeping yourself alive while diving. So yeah, it's definitely like something that we'd like to explore, in changing another way of like actually interacting with the robot underwater. And we didn't have a low-level obstacle avoidance controller until we applied this method. So this is our low-level obstacle avoidance controller.
So in this approach, like the user is forced to give feedback all the time, right?
Well, the user is, I guess the way we had it set up, the interface for labeling the data was a user would go through the video and decide whether this was a point where the robot should have done something different. And at that point on the video, the person can just say the robot should have moved left, right, up, down. So the user is free to label all the images, but we didn't do that. And I guess one thing that would be useful is that we didn't address in this work would be like to detect in which frames would the feedback would be the most useful. That will definitely be something to research.
You have another question. It's like, it seems that in the experiments done in the paper, as input of the policy, the images of one RGB camera were used. Then it is mentioned that human experts could provide waypoints to compute the trajectory that the robot should follow. How is the current system computing the depth of these waypoints? At the beginning of the presentation, it is mentioned that the robot has stereo vision incorporated in its front view, but it seems that currently it is not being used. Are there plans on testing this research also using the stereo vision system to tackle these types of possible limitations?
Right. So the two front cameras can be useful for obstacles that are really close, but not in general, like for 3D pose estimation. So we did experiments before with the stereo vision, and we had the problem that the baseline is a little bit too short. For localization for the waypoint navigation, what we do is the robot also has a downwards facing camera, and that with our behavior, the robot can stay on top of texture regions that are good for visual odometry methods like DSO. And then, so we use the downward facing camera to do a state estimation with DSO, and that allows us to do the waypoint navigation in relative coordinates.
Thanks. So I think we are already running out of time, but I will give the chance to the first two speakers to introduce their work, because I didn't do it at the beginning. So I will ask Andrea Bobu to quickly introduce your work quickly, and then Anis afterwards.
Thank you. Yeah, I was wondering about it. Right, so our work is called Less is More, Rethinking Probabilistic Models of Human Behavior. And we're basically taking a like kind of the traditional probabilistic model for human behavior that people typically use in robotics, which is the Boltzmann model. And our observation is that in the Boltzmann model, people choose trajectories, say, in the robotic setting with a probability exponentially proportional to its reward. And we're making the observation that, in fact, sometimes the probability of choosing some options is affected by the similarity that that option has relative to the rest of the space. So for example, if you want to go around a block, I don't know, or an obstacle, and say that you have a choice between like one trajectory going to the left of the obstacle or 3 to the right, the fact that you have those 3 like very similar trajectories to the right shouldn't reduce your probability of choosing the trajectory to the left. So you should think more about how can I adjust this probability based on the similarity that these 3 right trajectories have. So that's basically the model that we're introducing, just the how do we adjust for similarities between options.
Thanks, Andrea. And Anis, please. Thank you.
Yeah, so the paper is entitled Interactively Shaping Robot Behavior with Unlabeled Human Instructions. And the goal of our work is to allow human teachers to guide the learning process of a robot by using instructions. The main goal is to remove the need to predetermine the meaning of instructions. So the motivation is to provide more freedom to the teacher in the way he wants to use instruction signals. So we proposed a framework that we call TICS that allows allows the robot to simultaneously interpret instructions and use them at the same time for accelerating the task learning process. And the results that we observe is that even though the meaning of instruction is not predetermined beforehand, we are still able to accelerate the learning process and also to reduce the number of required teaching signals.
Thanks, Anis. So now we will have a break of a couple of minutes and then we will start the session with the invited speakers.
Okay, I think we can resume in the interest of time. Hope everybody got a chance to stretch their legs. Awesome. All right, welcome back everyone. We will now get started with our panel discussion with the invited speakers. First of all, before we begin, we would like to extend our sincere thanks to all the invited speakers and for very interesting talks. I hope all of you got a chance to watch the videos we had uploaded prior to the panel discussion, and we have a lot of questions for all the speakers, and we look forward to having a fantastic discussion. So a brief note on how we are going to go through this panel. We have some specific questions directed at each of the speakers, so we will start with that. We will go sequentially, and I request that all the other invited speakers feel free to jump in whenever you have a thought that you want to share. And for others, if you for the general audience, if you have any questions, please feel free to submit it through Slack or the Zoom chat. We will be monitoring those, and we can ask the questions as we go. And once we go through sequentially each speaker, then we will have a general discussion period where we will post general questions to the entire panel, and we can discuss these different questions and possibly debate over them. So without much further ado, let's get started. I think we just have a list here, so there's, and we will go through that. So we will start with Anka, if that's all right.
Yeah, hi. Hello.
Thank you again for your talk. So we have a lot of questions here. We can also forward some of them to you for you to answer them offline. So we will see how much we can get done given the time restrictions. One of the first questions we have here is, what are your thoughts on being able to handle the possibility that humans sometimes focus more on doing things that are feasible as opposed to being optimal? There's a lot of implicit choice that you talk about on how you leverage that power. Could you speak to what would happen if they just don't even care about optimality and they're focused on feasibility?
Yeah, so that's a great question. I think in our thinking, even though you're absolutely right, Harish, that most of our work is about learning reward functions and assuming that people are optimizing reward functions approximately. I think many of the ideas, even though we haven't implemented them that way, are applicable to constraint satisfaction, to a satisficing-like framework. And sort of that's because even if people aren't making an optimal choice, right, or they're a noisy optimal choice, if they say they're satisficing, you will have these, if it's satisficing, then it's basically epsilon optimal, right? So what is that epsilon? You don't know. That might be a parameter that you're trying to learn. And then the behavior that they have, right, every time they act, every time they give you this sort of feedback, any of the types of feedback that I was talking about in my talk, you're getting this so maybe noisy signal that says, well, this is an epsilon satisficing solution. Similar with constraints, right? You can have chance constraints, you can have deterministic constraints, you'll have these thresholds on them. You might have additional parameters on what they are. And similarly, you can think of human behavior as saying, well, probably the human behavior that I just saw, whether it was demonstrations or corrections or, the person turned me off or whatever, that was probably a solution that you can map that to a solution and say, well, that trajectory satisfies the constraint, rather than what I was talking in my talk, which is, we map it to a trajectory and say that trajectory was kind of a noisy optimal choice. And then the other thing that I want to point out is this really interesting connection that I think not many people realize, but I find it fascinating, which is a lot of times when we talk about people as making choices, like in inverse reinforcement learning, we're talking about this Boltzmann model for how people make these choices. So, or this Gibbs distribution has many names in different communities. You can derive that in many different ways, but my favorite way to derive it is actually as a satisficing solution. So my favorite way to derive it is to say, here's this reward function. People want to be optimizing this cumulative reward, but they're actually going to be epsilon optimal. And so you can say, what is the probability distribution over trajectories that maximizes entropy subject to the constraint that in expectation, the cost, the reward of their trajectory is epsilon optimal with respect to the reward. So if you write it that way, you can have the KKT conditions. Out of that falls the Boltzmann distribution, where that epsilon that you're saying, the pure epsilon optimal, that epsilon becomes the rationality coefficient in the Boltzmann distribution. So basically, there's more suboptimal people to be, sort of the higher variance that your probability distribution will be. So anyway, that's what I wanted to say. I think you're absolutely right, and I'm not trying to in my work make any kind of ideological distinction between is it rewards and pure optimization, is it constraints, is it satisficing. I'm just trying to say, no matter, if you take your framework of choice, no matter what you're trying to estimate, there's all these different types of feedback that you can learn from.
Okay, thank you.
Harish, you said at the first that we should jump in and make this a discussion, so I'm going to take you up on that. And so hi Anka,
hi Peter,
everybody, and thanks to the organizers for putting this workshop together. So on that topic, I think it is important to recognize that people aren't always trying to be optimal, right? And in fact for different reasons, right? So it could be that when you're teaching and either a person or an agent, if their behavior is not yet, they're starting from scratch, you don't need to be optimal. You just need to move them in the right direction. Mm-hmm. And so I think, it's worth making a distinction between the person is not acting optimally yet, but will move towards optimal as the agent gets better and needs that more refined signal, versus the person doesn't know how to behave optimally, in which case, you need either the kinds of stuff that Scott does on having ranked trajectories or ranked feedback, or else have some well-defined external reward signal that you can say, okay, I'm going to try to be like the person to get myself jump started, and then I'll learn from a reward signal that I know from the environment, which is what we did in Tamer with Brad Knox back a long time ago.
Mm-hmm. Yeah, and these corrections that we sometimes look at fall under that category because, depending on how you can think. So my argument is that we can think of all of these things as choices that people are making, right? But the question is, what is the choice set that they're choosing from? And so what's particularly related to what you were talking about, Peter, is with corrections, I've actually often wondered whether we should interpret them as, here is a trajectory that's better than the trajectory you were following. And that's just a choice between two things versus, here's a trajectory that is optimal. And it just so happens that it's a correction on top of the thing. It's just, I took your trajectory and turned it into something optimal. And we've looked at it both ways. We've implemented both. With ARMS, we haven't really seen a difference. I can't even tell you. But you're absolutely right that it's really important to get this choice set right. And I think one of the lessons for me in starting to think of all these different types of feedbacks as choices that people are making is just how easy it is to have choice set misspecification. Even in learning from demonstrations, we assume that there's a space of trajectories and we have common ground with the human on what that space is. I don't think that's true. People might not be imagining all possible trajectories that the robot could be doing, and therefore their internal choice set might actually be different from the robot. So
yeah. And I guess the choice set is somewhat, as you're describing it, is somewhat orthogonal then to, is the person trying to give reward or is the person trying to give advantage, right? That which is the coach from Michael Littman's group with Jane McClash, and that was like treating the signal that a person was giving in a feedback modality as advantage as opposed to reward, and that makes a big difference compared to treating it as reward like we did with Tamer. So good.
Yeah. So actually, the way we think about Michael Littman stuff, and I've been talking to him about this, is as a choice that the person is making. But the choice is actually, it's not when I tell you +1 or -1, it's not that I'm actually telling you the reward is +1 or -1. Well, I'm really making a choice between the trajectory that you have, right? Versus basically it's relative to the trajectory I was expecting you to have. And so
that's the advantage perspective.
Yeah, exactly.
Well, one thing I'll add real quick is, and I know Anka's certainly thought about this, is that when you think about these choice sets too, the way that you frame them, I mean, it's not really even necessarily with respect to what the state of the world is or what's going on, but it's really more about belief of the human, right? That they're sort of being optimal with respect to current beliefs, perhaps, or maybe not trying to be optimal, but trying to teach well or whatever. So that makes it sort of there's even one extra layer of indirection there for interpreting these sorts of things.
Yeah, that's absolutely right.
You, Scott, put a very nice point of what to believe that was the best way of understanding what the humans believe is best for the robots to learn. So actually, humans are building mental models of the of the robots, and they're using teaching strategies like scaffolding. Like they're first teaching the easiest part, and then after the robot seems to have learned that, they're trying to make them learn harder and harder stuff. And those kind of things that are usually not taken into account in the learning models.
Yeah, so I have one word of warning about that, Billy, which is we were looking at these we call them pedagogical behaviors that people might have. So the difference between showing or doing and sort of Michael Littman terms. But one thing that we've found is that it's really easy to get those models wrong. And so you're actually, so if you get them right, then taking them into account is super helpful. But actually, we actually even we fit model to data, and even in those cases, it was better to use the sort of the expert non-pedagogical model. Just treat the person as doing something simple. That's not what they're doing. They were trying to teach, right? So you take people who are trying to teach, you fit your best model of teaching to them. Right, it's still not perfect because but it's better as a model, as the descriptive model of human behavior. It's better than the model that says people are just making rational choices out of these things. They don't care about how the robot is learning. Now, you have these two models. One of them is more accurate, right? The other one is less accurate. The robot's inference is better with the less accurate one, because there's some crazy thing going on where the more accurate one is still not 100% accurate. And so increasing accuracy of the model, because you're running this inference, that's what you're doing with the model. So at the end of the day, you don't care about model accuracy, you care about how good the robot's inference is. It turns out the robot's inference is actually better when you're using the naive model than when you're using this pedagogical model, which is crazy.
But are you pointing out that the priors then are too strong? I mean, those are basically priors for the learning, right? Those pedagogical models, they're just priors of what. Oh, you can think in terms of priors, right? So are you talking about that you're putting kind of too much trust in your prior?
So the models that I'm talking about are ones where you say that think about it in a learning from demonstration context. The trajectory that the person is choosing, right? The naive model says the person is just choosing the trajectory with the highest cumulative reward. The pedagogical models are saying the person is thinking about how the robot will learn and is choosing something that is going to be the most informative to the robot. So it's kind of this difference between acting optimally versus sort of trying to be legible, pedagogical, whatever. You can look at human data of people trying to be pedagogical. You can fit a model to that data. So now you have a different probability of trajectory given reward. It's not that people are optimizing reward, it's that they're actually trying to be informative. And it turns out that those models are really risky to use because unless they're really good, they actually introduce wrong inference for the robot. So if you look at reward accuracy of the robot using the nominal like Boltzmann probability of trajectory given reward versus these pedagogical ones, you end up with better inference on the pedagogical ones. So there's not these there's no prior in the sense. I mean, the robot might have a prior over the rewards, but it's really just these. You can look at your maximum likelihood estimate of parameters that describe the human. Yeah. And what I'm pointing out is, those parameters better fit the actual human data. But when you use them to run your inference on what the reward is, you end up with worse inference, at least in the experiments that we've done.
Sure. So. But that's actually not so different from, because we need when we do greedy active learning, we're kind of trying to query the humans for the most informative thing, the questions. And when we do super greedy, we actually get worse results than if we kind of are less greedy. But it's more that maybe the pedagogical, like you said, when the pedagogical models are correct, they are super useful. But often they kind of, let's say that humans are optimally informative is probably a wrong prior, or it's a wrong model. And I think that at least what we say, it's much more important for the humans to be actually something that's in context. So basically maybe relates to a particular error that happened in just the previous, not in any of the earlier demonstrations, but just the previous. So there's a kind of, for example, the temporal sequence in which order you got the demonstrations has a big effect. Or that it can be that this is something that would be easier way of accomplishing the same thing. So kind of these, which are of course terribly difficult model. I mean, it's not at all easy to kind of try to model, or it's something that is easier for a human to capture, or it's an easier, let's say, mental model to represent something. But I think that so I agree with you perfectly that kind of maximally informative or maximal, let's say, reduction in entropy, whatever you want to put information theory criteria, is probably not the way how humans teach. But I think that's the point, rather than that I think we still should understand the humans. But I think there's a gap now in understanding computationally what are the decisions of how humans teach.
Okay. So
yeah, I'm totally on board with that. Absolutely. I was just pointing out that you can get more accurate models of how humans teach. They're literally more accurate than assuming the naive model, and your inference might be worse. So so when you go to these more sophisticated models of how humans actually teach, we just have to be a little bit careful to not make matters worse by going to a more accurate model, but actually it's not 100% accurate and it ends up biting us in the butt.
Okay, all right. So in the interest of time, I'm going to pause the discussion here, as much as we are all loving it. And thank you. It sort of covered several other questions that we had prepared. And then you also touched upon some stuff that I would love to come back to. So in the interest of time, we will go through the rest of the speakers and we will circle back to these concerns. I think next up we have Dongyu Lee.
Yes, that's correct. So. Hello, Dongyu.
Yeah, hi. Do you see me? Do you hear me?
Yes, see and hear, yes.
Yeah, hear.
Okay, so your presentation was called Interactive and Incremental Robot Learning. It was a very nice presentation, I think. We have quite a few questions for you at this point. So as before, I mean, all the other speakers are also welcome to intervene, of course. So the first question to you is, for shared teleoperation, how do you think the task should be split between the robot and the human? In other words, how to decide their respective roles? So you covered this partly in your talk, right? So I guess it would be nice to know as a more high level question.
Yes.
What is your take on this? I mean, how do you think is the optimal way, or the
right? So I think the usual choice would be, I think, if we could teach the robot already, right, some kind of autonomous behavior, then I think one way to do as robot does fully autonomously, but just a human is just supervising. Just a human monitors the situation. And then when robots think there is some kind of error or something deviation from what it has been learned, what it has kind of expected, but what it really observes in real time, that kind of thing can be warning signals, right? Either it can be using that kind of information to wonder human teleoperator to intervene, or just a human always take attention to the system, and then since the unexpected situation comes in, then you use kind of checking the energy flow of the humans putting into the system, and then authority goes to the human whenever human want to intervene. That would be one possible. I mean, I talked about question two ways, right? So one as human observe the situation, and then just take whenever he wants. So it's kind of human always have a possibility to overtake the control over from the robot. And also it only happens to the direction where he wants to do. So there are multiple tasks, in fact, right? There is, or if you can, horizontal task X, Y, Z, or orientation, whatever tasks are there. Or you can just say as end effector task, or it can be the nurse case task, whatever it could be. And then human just just intervene specific parts of the task at the specific part of the time by doing this kind of authority changing. That is one thing. And then another thing is the robot is trying to see what kind of anomaly happens and then tries to come back to the human and ask for help to out. And other approaches more often used in the control of domain is you also see that kind of accuracy of the sensors, or you kind of see a lot of visual occlusions. Then you also kind of decrease the authority of the autonomous parts. So these are the, I think, well-known, at least. I mean, I think the last one is more well-known approach, and the other two approach could be also very interesting.
Mm-hmm. Yes. So actually, I had. So I think it might fit in the second case because it's related to the uncertainties. But I think that the type of policy encoding that you use, it can also give you information about, for example, how confident the robot is about some parts of the task, right? Mm-hmm. How do you see this kind of information? For example, when you have probabilistic models, you can have information on correlations on variance and so on. How do you see this as a way to arbitrate this authority between the human operator and the autonomous system, the robot?
Yeah, I think basically human can also check what is when he need to take over, and robot also checks the autonomy he think he's kind of confident over, right? I think in fact there are two control sources are there, and they all estimate their certainties, right? And their confidences of the task. But I think one of the important thing is, of course, robot can artificial agent can check this kind of confidences and then using it for the decreasing or increasing its own authority, right? But also I think the important thing is a human should always have a way to even, take over the control, even in the case of the robot think I am super confident.
I was just going to say one thing I did like about that approach and your talk on Wave was the idea that that you can have safety in this way, that if the person can take over, then even during the training process, you have some kind of assurance that the person is going to not let the robot do the wrong thing. And at the same time, that provides a training signal to help it improve in the future. So you get sort of both of these at the same time, which I think is nice.
Mm-hmm. Yeah, thank you.
So maybe we could move on to another question. So one other question is how to simultaneously learn from different modalities of teaching. So this is a question from Harish. I think that it refers to the fact that typically people choose one single modality to teach a task by imitation, and I think that this question touches the point of what would be the way to consider the different modalities into a unified approach?
Mm-hmm. Yeah, very good question. I don't know. I don't know. I think one of the way I'm just trying to see is what this kind of teaching modality is good at, when they are good at, and when they are not good at, and then tries to combine those approaches, and then go for it. And then I think I see a lot from the human perspective, right? What is the most easiest option for the human? And then I think starting with that is also a good approach, because then it's kind of also reduce the cognitive burden or teaching burden for the human operator to teach the robot. And then, once robot learned general concepts, and then I think later on we can use a lot of this incremental learning or correction of the previously learned behavior. I think that would kind of reduce a lot of the burden of the human teacher. So that is the kind of way I see how to combine different teaching modalities.
This was the core focus of a DARPA program called Bootstrap Learning a while back, where the idea was to allow agents to be able to learn from lots of different modalities, some supervised, some unsupervised, and some from human demonstrations of difference. So people interested in that topic, I would advise looking at that program. It was about 10 years ago or so.
Mm-hmm. Yeah, I think this is a different learning approach. Is also good for the like teaching under supervision or unsupervised learning and so on. I think that is also good for the like looking into the effectiveness of or speed of the learning. But also on the other hand, when we talk a lot about the learning from the human demonstrations, then I think we can also think of one more aspect, right? Which is, I think, the intuitiveness and which is the cognitive burden of the human operator, human demonstrator.
I see. Thanks for your answer. So there is one other question. I think we still have the time. It's a more low level question in the sense of related to the approach that you presented. And the question is, what are the advantages of replacing the original nonlinear term of a DMP with a GMM?
You say again. You said like what is what?
Sorry. What are the advantages of replacing the original nonlinear term of a DMP with a GMM?
Okay, yeah. So I think I think of course the original approach of the DMP is also working well, but I think also people are using a lot now the DMP with GMM approach to only learn the forcing term. I think one of course a clear advantage would be you don't have to have too many basis functions also, because the Gaussian mixture models and such thing kind of allows you to place your basis or Gaussians, right? More optimally, so it kind of reduces the number of the parameters you really need to learn. So I think it kind of course, more the learning aspect, parameter aspect is more compact representation you can come up at the end.
Yes, from my perspective, it's. I agree. I mean, I think the main advantage is indeed that you don't need to manually select the basis functions that you need for your problem. So it has good advantages at that point. So I think it's time to move on to the next presentation. Thank you, Dongivi, for your feedback.
Thank you.
Thanks. So the next presentation that we'll be addressing is the one from Vili Karki. Vili, are you there?
Hi.
So thank you once again for your talk. Again, I think it was a very nice presentation about a topic that I specifically, particularly am interested in. We have 5 questions for you in total. Let's see if we can go through all of them. So the first question is, and I think this question is really perhaps one of the most central questions for your line of work. It's what would be your preferred approach for modeling human teachers? Would it be by injecting prior hypotheses about human preferences in the way you did with the human-aware strategy, or incrementally learning about these preferences by interacting with the human in the way you did for the learning preferences for temporal tasks? Did you understand the question?
I'm sure, but I can try to answer it. Let's say, so whether we want to have some prior models or whether we want to learn the models of human teachers. Is that the question?
Well, the question is more generally, how would you prefer, how do you think would be the best way to learn the models of human teachers, let's say?
Yeah, so I think that we can get really evidence from psychology and from cognitive sciences, especially when we talk about things like models about human memory, models about different human cognitive skills. And those, in cases, those are models that have been tried out in, let's say, over the years with multiple successful examples in various areas. Those are, let's say, relatively good models in some cases. Of course, there are still great simplifications we need to have, but those are strong enough priors that we should use those priors, because in a way, starting to learn human teaching behaviors or understand the human teaching behaviors just from data-driven point of view, I think that we don't have the easily data, especially if you don't have the data in a particular single learning setting. So we at least need more data in order to, if we want to at the same time model the human
teaching skill and human, for example, human performance in a particular situation. If we want to understand how, let's say, the sequence of questions or sequencing affects their correctness, it's really hard, because typically if the human is our own feedback, we don't get the feedback signal that will directly tell us that our model is improving. Mm-hmm. So for that reason, having priors that at least set the structure of the model, I mean, not necessarily its parameters, but at least the structure of the model of how the human teachers work, or how their brains work, how they which things affect the humans' correctness in their answers, in their demonstrations. If we have at least the structure of that specified, then we may be able to modify the parameters or learn the particular human teachers, adapt to their particular human the particular skills in both teaching and maybe demonstrating the particular skill. Mm-hmm. But beyond that, if you don't put any structural priors there, I think that it's an ill-posed problem to try to learn their correctness if we don't really have a nice feedback signal. We're just looking at the performance and their feedback in the robot's performance.
Mm-hmm. So what are the structured information you are feeding in?
So for example, that we know in this case, for example, as an example, in one of the papers I was referring to in our presentation, we have a model of human cognition, especially human short-term memory or human memory retrieval, that tells that if you are addressing something that which is closely associated to previous or short previous time, then it's you get a better retrieval. It's faster and more correct than if you are doing, let's say, context switches. So basically, you are asking always about different things. It's just that the human, it's tiring, and human especially over time, humans get tired and then they start making more errors, for example. So this is the structure, is that we know that if we are referring something recent, we are getting more correct answers. And that's the structure. We don't say how recent. Setting those parameters may be quite hard, but at least we know the kind of the trend, or we have a model for it. And then we may be able to optimize the parameters of that model, how fast we learn, how big jumps in the context we are able to make without the human suddenly becoming much slower to respond, for example, or that that is actually one of the kind of not direct or indirect ways of looking at their increased cognitive load, and that which is also typically indicates that they're more likely to make errors.
Mm-hmm. So maybe connected to this, to what you just said, and also perhaps to Don Huey's question. So the second question asks, what kind of models do you think we should focus on? For example, what variables to predict and use as input?
I think that's case specific. I mean, it's really.
If
you're talking about kinesthetic demonstration, we are talking about some kind of much more less embodied, much more abstract information. I think that the models would probably look quite different, but there are things that actually are still interesting, that we can think in terms of, let's say, the human memory. We are talking about things that are, for example, we did the one experiment where we had asked about different attributes about animals, which were about whether they are carnivores or herbivores, for example, which is a non-visual attribute. But we also asked about visual attributes, and there are differences when, for example, if you are asking about visual attributes, that does a particular animal have a tail, for example. Visual attributes typically give us much faster answers than these more abstract attributes, and that people are making much fewer errors even with large context switches with these visual attributes, because they can see in their head the particular animal. So even if you did a great context switch,
you would see the new animal in your head, and you'd be able to say whether it has a tail or not. But if you ask if it's a carnivore, people make, after these context switches, people make lots of errors. So it really depends a lot on the questions, what kind of information we are trying to extract from the humans. It depends on whether it's something that's embodied, whether it relates to a physical skill. One thing that humans are really bad at explaining is physical skills. I mean, kinesthetic skills are really difficult to explain. Like, how do you ride a bicycle? By just explaining in words, and then trying somebody else trying to do it just by the verbal is probably quite difficult. So it really depends on the particle. And I don't think that we have a particular single type of model that would work for kinesthetic teaching or the abstract attributes or maybe temporal sequence or some things. I think that those are different things, and we need different models.
Okay, thanks for your answer. So maybe we move on to the third question. In your interactive kinesthetic teaching, kinesthetic learning for demonstration, the stiffness is increased. So in the approach you presented in your talk, the stiffness is increased. How is that increase computed? What does it depend on?
In that particular thing, the stiffness increase was basically pre-programmed based on initial experiments. So there was not a particular, it was not adjustment to the particle demonstration. So it's just a fixed set of stiffnesses that were basically pre-programmed over demonstrations. So it's basically after each demonstration, you change the stiffness value of the robot, and there was a certain progression of stiffnesses.
Okay, I see. So another question regarding specifics of representation is that you also mentioned that models learned incrementally were superior. So what metrics did you base this statement on? So under what metrics is this valid?
So we had in one of the experiments, the humans had to basically try to replicate a template. So they saw a template, and when they had the feedback from the robot, when the skill performance, so basically their ability to replicate the template after a certain number of, or basically after any number of more than one demonstration, was better than if we just take the average of those demonstrations. So if you have multiple demonstrations, we still of course can clump them together and just basically in a way average them out, or fit a model that is on where the expectation let's say maximizes all of those in the expectation, and then replicate the skill, which is basically generates you the mean trajectory, typically, or depending on the type of movement privity or whatever. But you could think that it typically describes your mean or some kind of robust mean, depending on the distribution. That is, but when we had the feedback from the robot, so that people were able to see what the robot already learned, they were basically doing much better demonstration because they can concentrate, or part of it is because they can concentrate their kind of mental effort on teaching the part that is not yet learned. Is it clear, the answer?
I think also this kind of incremental way of showing the demonstration is helpful because then human really realize what robot really has learned or not has been learned, right? So human really can give a much better quality of the demonstration next round. I think that is the basically key of this, having bi-directional interaction during the teaching rather than just giving the batch of the data.
Yeah, I agree. That's the whole key of interactive intention learning, on like building on top of the already built policies or the knowledge that has been gathered. So I think now we can move to the next speaker, who is Dylan Lucy. He has presented this work named Personalizing Robots to Learn Latent Actions. I really enjoyed this presentation. But the first question I will do is going to move to a different area a little bit compared to what we have been talking before. This regarding to the user studies. So we try to cover all the aspects in this domain. So in your experiment, you have designed this Likert scale service for the subjective measurements. But like, I wonder, how, like, is there like particular protocol that you follow for designing this, or like, what do you think this, like, personalizing this service compared to some already existing service or questionnaires that are around that are used by the community of human-robot interaction?
Yeah, great question. Hey, Carlos. And yeah, thanks everyone for coming to the workshop, and thanks for organizing it, I guess twice, once for in-person and then once again for this virtual workshop. So the work I presented is all about trying to take high-dimensional robots with all these different degrees of freedom and make it so that we can easily control those robots using a low-dimensional interface, like a joystick. And the applications were kind of in assistive robots, where we might want to control a wheelchair-mounted robotic arm with a joystick attached to that wheelchair. So we did some user studies, not with our target population, but with able-bodied users in the lab, trying to control fetch and Panda robot arms that were doing cooking and eating tasks. And as part of this user study, like you mentioned, Carlos, we asked the users questions about their experiences. So at the end of the study, what did you think? Like, did you like this particular interaction method? What about this other interaction method? Was it easy? Was it intuitive, etc.? And so when we choose these questions, there are a few like paradigms that we want to keep in mind to make sure the questions are fair and representative. The first is, in this Likert scale survey, we always try to ask questions in pairs, like a positive statement and a negative statement. So it's like, the question might be, I found this to be intuitive. And then the next question would be like, I was confused by this particular strategy. So that people have a chance to answer both different directions. Other than that, I completely agree that there are like excellent standardized surveys, some from NASA and other organizations, that certainly do make a lot of sense. And I think it just depends on the experiment you're doing, whether you'd want to use one of those, or perhaps you have some questions in mind that are really relevant to your work that you want to make sure you ask. And perhaps a combination also makes sense. But I do think Likert scale surveys have like a strong historical significance, especially in psychology communities. So I think they're pretty worthwhile.
Okay, thanks. So we have a second question that is by Andis Nayar. To what extent does the latent actions approach depend on the similarity between the state of the environment during the data collection and during the task execution? So this is more about the generalization of your latent action space.
Okay, yeah, generalization is like definitely a really good question. Something we're still trying to understand exactly how well this approach generalizes. The idea is sort of that we're going to provide demonstrations at training time of things that might be useful for the person when they want to control the robot. So, in this cooking task, we showed it things like moving between shelves, stirring, pouring, skills that we thought might be useful for the robot to do when the person was trying to control it. But at the end of the day, the user is still in control. So it should be up to them to decide what the robot does. And so there's certainly a trade-off between providing these demonstrations and showing the robot like a variety of different things that it might want to do, and also making sure that we can successfully embed all these different skills to the latent space. Because as you might imagine, if we keep trying to push more and more skills into this latent space, eventually it becomes really unintuitive for the user to use, or the latent space throws away some of these different skills as noise. So we found two different ways to improve generalization. The first is that when we're trying to reconstruct these high-dimensional actions, we make sure that we condition on the state that we're currently in. And I think in the talk I gave the example, imagine you're holding a glass of water, maybe some things you might want to do with that glass of water, or like pour it, drink it, put it down, etc. And so there's kind of some, based on the state I'm in, I've kind of got some insight into like what actions I might want to do. Whereas if I'm holding a doorknob, I probably don't want to pour the doorknob or drink the doorknob. So context gives me a lot of information that does help me generalize using these small latent spaces. The final thing I'll mention on this is that although I do think latent actions are like exciting, there are also some really excellent existing approaches that we can use as well, so that perhaps when the latent actions fail or we can't generalize this new task, maybe you want the robot to throw a baseball and the robot has no idea how to throw a baseball. At that time, it might make sense to revert back to another scheme so the person can then maybe control the robot directly, move the end effector, etc. And I think there's a nice sort of balance between using these latent embeddings and then trying to fully control all the joints of the robot when the robot does get confused.
Thanks for this answer. So next question, it says, for the latent actions only case, how do you consider the matter of generalization for different state actions? For example, you mentioned the actions of picking up a mug and grabbing a door handle. Do you need specific demonstrations to each case, or is there some transferability of the learned state and action pairs? So it's very similar to the previous one.
Yeah. Another good question, but it does bring up another excellent point. I think it kind of depends on how you parameterize your state space in some sense. If you were to say that every type of cup falls into this particular object, like you were to categorize a set of objects as cups, then you could generalize across all those different cups. Another thing though that we have done in the work is considering if I learn sort of how to work with one goal or one object in the space, I can then transform, mostly in a geometric sense, transform what I've learned from one goal to another. So if I've learned to pick up and manipulate one cup, I can then take what I've learned and transpose it to a different cup that's in the workspace that the robot can see that maybe wasn't available at training time, but is available at testing time. So I guess I don't want to make any strong statements yes, I can guarantee we will generalize, but so far we found some success using either parameterizing the state in an intelligent way or thinking about how we might be able to transform between different goals in the space that we recognize.
Maybe something, a follow-up question that I have, because you mentioned that you work, your motivation is also assistive robots. So with these latent actions in lower dimensions, you are also constraining. So actually maybe you are kind of indirectly ensuring safety, right? Because
that's an interesting point. So what we've been doing more recently, and sort of the second half of my talk I mentioned, we're trying to combine these latent action approaches with shared autonomy so that the robot can blend its own decisions with the human's decisions. The idea being that maybe I'm trying to reach for this cup and I can use these latent actions to direct the robot towards that cup. But as the robot sees oh, you're trying to go to this cup, I can help you with that. It can then provide assistance, maybe making my job a bit easier, or once I reach the cup, it can help maintain that position. And so I do think, just Carlos, your question is excellent. I think building on that question, this idea of maybe using shared autonomy in addition does provide me some safety constraints. For instance, in the paper, we found that we have uniformly ultimately bounded stability about some goals that the human might have in the space, where the size of those bounds depends on the robot's confidence in that goal. So we can at least guarantee that maybe we're in some sort of safe set. And the other advantage of this is as long as I'm staying closer to these goals, I've seen demonstrations on those goals. So it's a place where I can generalize well using my latent space.
Okay, thanks very much for this answer, Alex. So I think we are good in time now. We have to move on to the next speaker, who is Scott Nicholm from University of Texas at Austin. He presented this work called Probabilistically Safe and Correct Intention Learning. So we have 6 questions here, but I think all of them are very similar or in the same topic. So I first will throw the question that is more different, and then we go to the same topic. So Anis Najjar asked, how well does T-Rex perform compared to standard RL algorithms like DQN or any other?
Yeah, so I think there's an important difference to sort of point out there, which is that, what we're trying to do with algorithms like T-Rex is work in the purely imitation learning setting. So, looking at when we have demonstrations and then trying to infer a reward function, then do RL on top. And so, something like DQN could be used after T-Rex to optimize the reward function we find. We use PPO in the paper, but you can sort of swap out whatever you want in there.
Thanks very much. So next questions are more related to, I will phrase the question of Harish. So what are the implications of not accurately knowing the features of the spec policy? Could we learn them actively? So I think in general, I think these approaches that you have presented are very sensitive to the state representation that you have, the kind of features that you have, right?
So Well, let's see. I think I'm going to hijack this question a little bit to push some of my larger agenda on imitation learning. So, our method it's one of the few, if not only, sort of imitation learning algorithms, or at least ones that are doing reward inference that don't require sort of knowing the features, that the expert was using. And I think, this is really important to not necessarily make assumptions about what the person was using, or that they were linear and some specific set of features. We just have rankings over demonstrations, and then we learn both features and functions of those features that explain the ranking, so that we can extrapolate beyond the suboptimal demonstrations that we might have seen, which I think is really important and much more in the spirit of IRL and sort of understanding the motivation of the person. I think seeing that that curve, or being able to extrapolate and saying this is what's making the demonstrations better and better, is both connected to explainability, and is also more in the spirit of saying that we understand the person's motivations as to why they behaved in a certain way. As long as the agent has access to the same underlying inputs that the human was able to observe, we don't have to know the exact features that they were using. And this has lots of other side effects too, I think. Anka talked about, Boltzmann assumption earlier. And I think one really nice thing about thinking about demonstrations in terms of preferences over trajectories is that now, at least in the way that T-Rex models it, we don't have to make assumptions that the person, was behaving Boltzmann optimal or Boltzmann rational. We only have to assume that they're able to specify preferences, essentially, in a Boltzmann rational way. So if two trajectories are really close together, there's, reasonable probability maybe that they're going to make a mistake and sort of get the preferences swapped. But for trajectories that are really far apart in how good they are, they're very unlikely to do so, sort of exponentially more unlikely. And this seems like a much softer and sort of more reasonable assumption, perhaps, than assuming that somebody is Boltzmann rational. And it also allows us to learn from demonstrations that could potentially be really quite highly suboptimal.
I really like this idea of the assumption of or having very limited assumptions and making it the system to learn everything, or as much as possible. But I was wondering with respect of this, if you don't have any particular features or state representation, the extrapolations that you can get, you can get many extrapolations, right? And then what I saw, I was very impressed with your results, but I was wondering, with the demonstrations that you got, or these rankings, you could get other extrapolations that might fit these rankings as well, but they are very different to what you actually obtain. So for instance, you have this, you showed the Hop-Cheetah learning to walk, and you had 3 different stages which were ranked. All of them were falling down, but the ones that had better rank, they were walking faster. So then you show from this ranking you could learn. But also I think a good extrapolation of this is that you can learn to fall faster, because in the demonstrations it was not seen that actually the keeping the balance was the objective. So I really wonder how to control this, because I think in any problem you could always have different possibilities.
Yeah. So we've thought a lot about this. This is a great question, and it is definitely a problem. So I think the easiest domain to talk about this in, well, there's a couple, and I think they show different things. So one is Space Invaders. So as you do better in Space Invaders, you typically live longer. As you live longer, the shelters you hide behind get shot up more and more by the aliens. And so one way of sort of explaining the ranking of the demonstrations is that as the demonstrations get better, those things you hide behind get more and more shot up. And if that's the reward you learn, then the agent just learns to sit there and shoot the shelters instead of trying to kill aliens, right? It just looks for any old feature that explains the ranking, right? And so then the question is, how do you deal with that? type of that same sort of issue is when there are multiple features that are important. So in Mrs. Pac-Man, for example, it's important to avoid the ghost. It's also important to eat. And in fact, you're really avoiding the ghosts in service of eating. But sometimes it'll just grab on avoid ghosts and it won't try to actually eat food. And for other things, where you might not have something that just always increases monotonically and is always better and better, you can certainly worry about what the idea of extrapolation really means. So if you have a domain where not eating at all is bad, eating some is good, and eating too much makes you sick, if you only see demonstrations on the upward part of that curve where eating more and more is better and better, you're just going to try to, eat as much as possible. Whereas as long as you're okay if you see demonstrations where it starts to go down again, because then it'll probably learn to extrapolate along like a quadratic looking feature that makes you sort of eat the proper amount. So anyway, we've thought a lot about this. How do you learn features that are going to do this? And I think we have a couple answers. One, we have a paper that just got accepted to ICML a few days ago on a Bayesian version of T-Rex, where we actually think about risk. And so we think about all the different reward functions that could be true. And then we try to, for example, optimize a policy with respect to some risk measure over that distribution. And so for Space Invaders, it might say like, well, even though one possible reward function that would explain this is just destroying the shelters, other possible reward functions, say that, shooting the aliens is what's important, or living a long time is what's important. And, it's still hard to sometimes tune the amount of risk sensitivity you want to have to make this work well. But we have some promising results showing that, thinking about it in the Bayesian sense and trying to optimize with respect to that whole distribution helps us find things that are pretty good across the whole distribution and tend to sort of be more correct. I think another thing, though, is, that we're eventually going to have to figure out how to bring in prior knowledge from other tasks and just be able to think about, like, especially with robots and human situations, what are the kinds of things that humans typically optimize for? And so, a robot should not just say, based on raw inputs, what's the most likely thing that was being demonstrated, but also, like, and this is connected to explainable learning, is there an explanation for it? If the most likely thing based on the data is that, I wanted to be exactly set down the cup exactly 3.4 inches from, a corner of the desk or something. I mean, is there any reason why a person would want that compared to, setting a cup near a plate where they might want to drink from it? Like, thinking about downstream consequences of information outside the demonstrations, like, given the scene, why did the person give you this demonstration in the first place? Like, what's the thing they're going to do next after the robot completes its task? Why did they want you to do this thing in the first place? And that's a little bit outside the purview of sort of how we typically think about these things. Slightly related, like, there's a piece of Anka's work I really like, where they thought about, like, if a robot just walks into a room and sees, how people left it, for example, like, I might be butchering this, so I apologize, Anka, but, like, what can you infer from just seeing, the state of the world? And, if there's a vase on the table, for example, like, there are so many actions that could knock it off the table that it seems purposeful that, the person did not knock the vase off the table. And kind of thinking about things that are not explicitly seen in the demonstrations, I think, is going to be really important.
Okay. I think in the interest of time, we will pause here, but of course I will let Anka finish her question. Yeah.
Thank you. No, I wanted to comment on something that Scott mentioned a little bit earlier, which is, plus $1 million to this notion of actually keeping uncertainty about what the reward is. This is, if I could summarize what I've learned about reward learning in the past 5 years, is probably that it's really important to actually have uncertainty about the reward rather than go with a maximum likelihood estimate or a map, because there's really a lot of ambiguity. Even if you're using known handcrafted features and a linear combination thereof, there are going to be many things that explain what you see. And so, kind of back in this bit of what I would call inverse reward design that I'm always super excited about. That's sort of the key thing that we found is even if the person actually gives you a full-on reward function, they still only looked at a number of environments where they were actually that they base this on. And so you kind of have to think about what are all the possible reward functions that are consistent with that bit of data that you got. And it's the same with demonstrations, and Bayesian IRL has taught us that. But I think the surprising thing is, yes, when you go to this belief and now you're doing risk-averse planning, you can really hedge against various options because you're not just committing to one, and that could very well be the wrong explanation rather than right explanation. But I think there's a big cost to this, which is what I wanted to ask Scott about. We tried to do this for sort of raw feature spaces as well, and sort of representing the reward as a neural net defined on the raw feature space, and do some variational inference. And the challenge there seems to be that I think Scott picked some really sort of intuitive examples. Oh, you could learn that it's good to hide behind these things or shoot at these things rather than the actual intent. These are still interpretable things. The wacky thing that happens when you say neural nets defined on state is that there's a ton of things that I can't even put in words what they actually mean, right? There's all sorts of spurious, this pixel with that pixel, bam, that's the answer. And when you go and you have a belief over that, yes, you might capture all of this, but it seems like risk-averse planning will just be stuck being not hedging its best against every possible thing. So we found that at least in our work, we couldn't actually push risk-averse planning to be the answer. You have to kind of go back to the person and leverage this uncertainty to get more data. But of course, the bigger your neural net is, the more data you need from the person. And it just seems to be some sort of, really fundamental problem here that I don't know how to solve, other than maybe what Scott was saying with, priors and, stuff like meta learning, where you say, there's a bunch of stuff that I've seen, so I can kind of figure out a feature space that seems to encode the kinds of things that people care about. But yeah, it seems like uncertainty is really, really, really helpful. But at some point, if you match that with raw features, then you start to get in trouble. Scott, do you have thoughts on what, in this ICML work, what was the answer?
Yeah. So in the ICML thing, the way we made it work was we actually needed to make things really efficient when we're doing MCMC. We actually needed a bunch of nonlinear features of state, but that we could take a linear combination of later. And so what we did was pre-train the neural network with, I think it was like 5 or 6 different auxiliary tasks, things like forward dynamics prediction, inverse dynamics prediction. And we trained them in a way that it forced the final layer to be linear. So it had to learn a bunch of features that could be used linearly to predict all these different things. And that sort of helped us get toward the types of features that we think we want. But in that case, it's really hard to know that you have all the right auxiliary tasks. B, just because something can linearly predict dynamics doesn't mean it can linearly predict reward. There's all kinds of problems there. I think as far as there being just lots of weird, spurious things that can explain things, I do feel like a lot of that stuff falls into the tail. And that's one reason why a risk measure like value at risk is nice, because it's not actually capturing how bad the tail gets. It's just looking at that cutoff. And that can be seen sort of as, feature or a bug. And in fact, recently we've been using conditional value at risk because we think it is more accurate. And it's also a coherent risk metric. And it's also convex and easier to work with optimization. But it does take into account how bad that tail gets. And like you said, when you're doing anything risk sensitive, that can just make it, way, way over conservative. And I guess I'll say really quickly that one thing that's really hard about thinking about risk is that you can't just think about risk. You have to sort of trade off between risk and expected value. And so, if you can take on a tiny bit more risk and get a ton more expected value, that usually seems reasonable in most domains. Whereas it doesn't make sense to take on a ton of risk for only a small gain. But setting those kinds of thresholds are also really challenging. So I guess the answer is I don't totally know what the answer is to this feature problem. I agree that a lot of it's going to come from priors and maybe even from sort of causal modeling and trying to find features that sort of have causal explanations of how the domain works, which I guess is kind of also connected to this forward inverse modeling idea. But yeah, it's tricky for sure.
The reasoning about risk is it's intuitive, but it's fraught. I mean, the setting that sort of drives that home for me is when you think about driving. If you only took actions that had no risk, you'd have to stay still all the time because
worst case you definitely don't want to think about risk in that way. I agree.
Right.
Yeah.
Okay. Thank you. That's fantastic. Of course, there are several threads there to sort of pick at. So we will come back to that when we have a general panel discussion. So for now, let's switch to Peter Stone, and we have a lot of questions here. And looking at how things are going, I don't think we will get to everything, but we will cover as much as we can, and we can always do some stuff offline. Okay. So you talked a lot about Garrett and your work. You guys talked about how you are able to learn from other agents using different things. One of the first things you talked about, which I thought was very interesting, is trying to take an existing navigation stack and being able to just tune the parameters. Because, of course, anybody who's worked with ROS knows those frustrations of getting the robots to do stuff, right? So it was pretty cool. I was wondering, do you think the pipeline that you have envisioned, that you basically take some demonstrations and optimize these parameters to work on different contexts and things like that, how difficult is it, or how trivial is it if you want to extend it to, let's say, a manipulation stack?
Great. So yeah, thanks for the question. And before I dive into that, let me just take the opportunity to thank the organizers, Harish, Carlos, Joao, for bringing this group together. It's a great topic, and it's a lot of work to organize a workshop like this. So thanks for that, and also to all the other speakers. I learned a lot from watching watching your talks. I thought it was a very interesting set of contributions to this workshop. Maybe I should also give a little context for why I don't look like the person who gave the talk. So Garrett Warnell, all the work that was discussed was joint work with myself and Garrett Warnell, who's a research scientist at Army Research Lab and embedded in my lab here at UT Austin. And we've co-advised all the work that was described there. His wife had a baby just a couple days ago, so he's not able to be here for this session. But we worked together on the talk, and then I'm agreed to be here to field the questions. I don't know how many of the people on the call watched all the way, watched the talk, but so to give the just the summary, the context is there were sort of two parts to it, and one was the one you just described, which I'll come to second. The other is an imitation from observation focus, and that's joint work with Faraz Tarabi, who's here on the call as well, a PhD student. And the context there, just like Scott was talking about, trying to learn without knowing what the features were of the demonstrator. In this case, it's trying to learn without knowing what the actions of the demonstrator were and not having access to that. So a state-only stream of demonstrations, and we use the generative adversarial method, extending some of the work of Stefano Urman on Gale that uses generative adversarial inverse reinforcement learning or imitation learning when you do have access to the actions. This was now when we don't have access to the actions and are looking at a state-only stream. The first part of the talk is joint work with Shuai Zhao, who's here on the call, and Bo Liu, was very much like you said. It was motivated by this idea that you often have underlying controllers that can behave confidently at a task, but that need parameter tuning. And so the work that we presented in particular, Apple D, was using the ROS navigation stack and actually multiple different ROS sort of underlying navigation modules, E-band and DWA, and observing that they have safety features embedded, but tuning the parameters is very sort of time consuming and difficult. And so we find that we can leverage this demonstration of a person and then try to fit those parameters that will follow the demonstration as quickly as possible, but still keep the guarantees or the desirable properties of the underlying stack. And so your question is a great one. We tested it only in navigation, and manipulation. You asked, would it be trivial to move it to a manipulation task? Nothing with manipulation is ever trivial. So manipulation, I think, is in general a much more difficult task than navigation. On the other hand, Apple D is a black box optimization method. It's and so as long as you have as long as you do have an underlying controller that's, it could be that can handle, manipulation, but needs parameters to be tuned, then it could. There's no reason to, no reason to believe that this kind of a methodology could work. And I think there's a lot of advantages, especially as the task gets more complicated, to trying to learn within a sort of regimented control space, rather than trying to learn directly at the control level of the the motor signals of the robot. And so that, I think, actually very, very much, if I were going to try to apply this to try to leverage this research towards manipulation, I think Apple-D would be a great starting point.
Can I ask a question? So
yeah.
How do you choose a parameter to optimize? What kind of parameters do we know? How should I choose? What parameter should you look at it to optimize in general?
Yeah, so that's a great question, and this is something that I've wrestled with in lots of different contexts. Both also learning robot soccer players, where you have controllers, and there's usually huge parameter spaces. Usually, and this is sort of a practitioner's point of view, I think, as opposed to a purist's point of view. But I think often, when you are trying to implement a method like a navigation stack that has a bunch of parameters, there is intuition for which are the ones that are most sensitive. That a person gets you can even just with each parameter do a sensitivity analysis and say, if I double or half this parameter, how much of an effect does it have? That's sort of one method for doing it in an automated way. But I think usually you come in with sort of a notion of the sampling rate is the difficult one, or the speed is the difficult one. So I don't have too much more to say about that. But maybe if Shueishu, if you were here on the call, maybe you can answer that question specifically for Apple-D. What if you can give insight into how the parameters you chose when you implemented this. I don't know if Shueishu is there or not. Yeah, are you there?
So basically for the particular work Apple-D, one thing is we designed this for the practitioners. So they don't actually need to know what parameters to tune. So the good thing is you can just tune all of them. And if Apple-D is able to figure out what is not very important, so we don't really need to tune that much, and what is important. That's for the practitioner. And for the system designer, they have insights into which parameters are important. So if they want to use Apple-D on top of their existing work, they can set these parameters in beforehand for the users. So basically in the field, when the users are using their product, it is very easy for them just to use the already preset tunable parameter set to run Apple-D on. Yeah, so this is a very good question. So we got asked for this question a lot, like how to choose the parameters. So the short answer is hopefully we don't need to choose. But the practical point of view is hopefully the system, the underlying system designer can already choose that for you in advance.
And I would say there's sort of this sort of two settings. One is where you can try to optimize all the parameters, and because there's few enough, and then like you say, the method itself can choose which are the important ones, or you can do this sort of pre-processing sensitivity analysis, and combined with intuition. But I agree, it's a great question.
All right, great, thank you. Okay, so next we have this question about the modality of. Either if it's the first part of the work, it's about what modality you can get feedback in. If it's the second part of the work, I think it's a little more interesting there because you're especially trying to learn from observations without assuming a lot of structure. Could you speak a little bit about what is your view on how one could choose one or how you could process high dimensional streams?
Yeah, so in the work that we presented in this particular talk, the modality is all demonstrations. In particular, either state action demonstrations or state only demonstrations. But in my lab and in my research over the years, we've looked at many different, and I mentioned already earlier in this presentation, Tamer, which was Brad Knox's thesis, which introduced the concept of learning from positive and negative feedback. that's, I think a very important modality, because there's situations when a person can't really demonstrate. For instance, I can't demonstrate to you how to fly a helicopter, but I can tell you, I can give you positive and negative feedback on, your flight is making me sick, or I'm enjoying the ride, or something like that. So I think this positive and negative feedback modality is important, and advice is another modality that's important that we've also done some work on. And I think it's we also, as was touched on earlier in this panel, the idea of being able to have an agent that can learn from all of these at the appropriate time, this sort of bootstrap learning concept. I think that's is and still remains sort of a holy grail of building robust and general interactive systems that they can learn from whatever modality is given, and it's really often a function of the domain, of the user's knowledge, of the user's experience, of the communication channel that's available between the expert and the agent, and we'd like the agent to be able to leverage all of these. And so I think it's sort of there's fantastic work talked about by all of the different speakers here. And I think, as a community, it would be great if we can find a way to put all of those together into a unified architecture and be able to leverage, the work that everybody's talking about that touches on sort of somewhat different points in each of these modality spaces, but all of which are very important, I think.
All right, great, thanks. Okay. So I have a quick question for the panelists. So we can start looking at some of the general questions. Actually, we have a ton of them, and we also have opened up several avenues for discussion. Would you all like a 2-minute break before we start with that discussion, or can we move forward? We can be flexible.
I'm okay to continue, but it depends.
Yeah, happy to go now.
Okay, so
I think everybody, I also should, I thank the organizers. I should thank all of the people who are here, remaining here through the workshop, despite the fact that the NeurIPS deadline is less than 3 hours away at this point. So that's a sort of a unforeseen scheduling change since this time was picked. But so thanks everyone for being here.
Yes, thank you indeed. And I also wanted to remind everyone, as we discuss some general questions, feel free to post your questions, whether be it on the Zoom chat here, or on the Slack group we have, or even on the YouTube stream. Whatever you feel comfortable with, please feel free to pitch in questions as they come up. We do have a lot of questions to go through from ahead of time, but we would be happy to take more questions as we go. Okay, all right. So I think I guess if Carlos and Joao don't mind, I can start with the first question and we can go from there.
Yes.
Okay. All right. So I suppose I will start with something which I'm not sure if it's going to end up as a debate, but nevertheless, it's an important discussion I think we should have. So this is about how much structure you would put into models of learning, and where your stance is with respect to the spectrum of designing hand-specified perfect controllers with Lyapunov stability analysis, and all the way to deep learning models where you are able to take a lot of data and be able to learn very complicated skills.
I mean, I think the way to think about this is sort of exactly what we were discussing just before. Is it, there's a practitioner's viewpoint and there's a purist viewpoint, and I think right now, if you want to get something to work with relatively little data and relatively little computation, don't do end to end. I think it's a fantastic question right now that the research community is asking, which is, what can you do with end to end learning? What are the there are clearly limitations. It's not going to, I don't think it's going to solve everything. But I think it's a great scientific question to understand what can it do with how much training data and how much computation. But if I were faced with a problem on the ground that needs to get, we need to get working in a startup company or in an industrial application, I would put in all the structure that I can and isolate what are the key points, what are the key parameters that need to be learned, what are the ones we already need to, what we already know how to do with, and put as much structure as we can in place to be able to make it work efficiently.
I'd also like to add that, I think, it doesn't have to be one or the other. And, I think you can have the complete advantages really of both. For example, by doing something like guided policy search, I think is a nice example where, you take, LQR controllers and use them to bootstrap, learning in a neural network. And so the final thing that you're learning is this sort of end-to-end policy. And then you can go and, tune that even without the underlying LQR controllers. You can get sort of the full advantages of an end-to-end and, highly parameterized system, but, help get up there with, well-known things from control theory. And so, I don't think we necessarily need to choose, although I do see it in some ways as being akin to, thinking in like the generative versus discriminative models thing where, in really low data regimes, it makes sense to impose a lot of priors and have a generative model, and in lower data settings, it often makes a lot more sense higher data settings, it makes a lot more sense just to have a discriminative model.
Yeah, I think maybe end to end is sort of a red herring. It's do you inject knowledge or do you not inject knowledge? And there's multiple ways of injecting knowledge. One is by using the structure, but still keeping it, like an LQR model, but keeping it end to end. The other is breaking it up compositionally into components. But both are just different ways of injecting knowledge into the system to be able to make the learning problem more tractable.
Yeah, if I could add, I completely agree. And one kind of train of thought that I've been using a lot recently is kind of a separation between offline and online, because the settings I'm thinking about often have like a human in the loop. And so I recognize I can't gather tons and tons of data from this specific person, but I could train a strong prior offline or come up with some baseline way of performing this task. And then work with the specific person, maybe someone who has a specific disability or specific need, maybe for a shorter period of time, and personalize this model that I've learned. That could be more like end-to-end, let's say, for the purposes of conversation, and then sort of fine-tune it with the user in mind. That's just one way that I've been thinking about it, that maybe sort of building what we've said combines both of these different aspects.
So I also think about this structure, putting the structure in the learning was a bit different context. Like when you think about like a lot of actions or movement primitives, or versus really doing complex tasks, dealing with many different objects like daily activity routines, then it's a different level of tasks, right? And then I think in such kind of cases, we might want to have some structure which also relate to the symbolic reasoning and so on, this contextual understanding and so on. I think this is also a different type of learning compared to that, learning how to navigate or learning how to reach and so on. So I think there also we need to use different structures, and it can be also different learning approaches. It can be merged together.
So I have like something to add to what Dylan said, like end-to-end learning. I mean, it's challenging, so I think that's like nice because we can like really stress how good are the algorithms. But on the other hand, we have the users teaching, and the users have like there are too many human factors inside this learning loop process, and end-to-end normally requires a lot of data, and it means in practice a lot of time for the user to give any kind of feedback or any kind of corrections or demonstrations or evaluation or ranking or preferences. And then in parallel, we have to take into account the usability of these methods. So, I mean, in research, there are many papers or studies in which we evaluate these methods and compare these methods to other methods using Oracle. So actually, there are not users or human users there, but they are replaced by any other agent. And we assume that this agent could work as a human, but in this case, we are not measuring how difficult it is for the user. Then when we go to reality, it is much more complicated, and we have to like reduce the complexity of the tasks that we evaluate with the humans, and we have to control a lot of other variables with humans. So I think that in principle, it is not so convenient to actually execute with users, especially users that are not experts on or they are not engineers, or they don't know what is going on behind. Because that's a point that we went also with injective learning. And we would like non-expert users teaching these agents to do something with these different kinds of sources of feedback, even when these users are not able to demonstrate it, but they can, for instance, give the rankings or preferences. But we are constrained to time, plus also the robot itself. I mean, also again, we can go to OpenAI Gym and do thousands of repetitions with an oracle, but then with a real robot in a real scenario with a user, it's harder to do this. So I think it depends also, we have to take into account applications and usability. So maybe we can move to another question. Let's see, we have so many. Yeah, maybe talking about oracles. So maybe this is more intended to do experiments and measuring again how good is a method. So before running actually user studies, it is important always to do preliminary tests with oracles and observing that everything is okay before we actually invite participants to experiment, and we explain everything and we set up everything. That takes a lot of time and is expensive and limited. For instance, nowadays we cannot run any user study because there is the confinement due to the COVID-19. So what are your thoughts about building oracles? Because building an oracle in interactive learning means something that is simulating a human, and there are too many variables that we have to take into account for simulating a human. So
personally, I think it's a trade-off between rigorous measures and realism. So the oracle allows us to sort of do repeatable studies and to measure over and over again, and because yes, user studies are a pain, but they're never going to be realistic. They're never going to be it sort of goes back to the noise in the real world isn't Gaussian. All simulations and models assume Gaussian noise or some kind of structured noise, and so we think about these same issues also in the sim to real community. When you're trying to learn in a simulator and make it work on a real robot, there's a trade-off between using an actual real robot as the target for the transfer from your simulator, or using just a different simulator. And if you use just a different simulator, you can still do a lot of the same studies, and it's repeatable, and you can get a sort of a ground truth sort of a baseline of how well you could do if you were if you trained for tons of time in the new simulator. But it's never going to be the real world, and so I think this comes up in not just this community, but across all over. There's this trade-off between repeatable measures and scalable experiments versus realism, and it's something we have to struggle with. We're never going to be able to simulate people as with an oracle. It's never going to be exactly the same.
I think another aspect that's really useful is for falsifying hypotheses so that you don't have to try testing them in the real world. So, if something works with an oracle, it doesn't mean it's going to work, with people because of all the additional complexity. But if it doesn't work with the oracle, then you've gotten rid of that, and it's not something you have to waste your time testing. So I feel like, aside from what Peter said, that's one of the biggest things we use it for.
Yeah, although it's not logically true, it's possible that something that doesn't work with the oracle would work in the real world because of the differences. But yes, that's the methodology we use, and that's a great point.
Yeah, I think kind of like the last question, the answer to this one is a bit of both. It's great to use an oracle or a simulated human to tease out maybe best case and worst case performance, or what happens when the human has this type of noise or they make this type of pernicious mistake, which is certainly very advantageous when I'm reading a paper to see okay, this is how it works. But then of course that's no substitute for a user study, which might have fewer numbers, but you can really see how people interact. Plus a nice thing about user studies is you get to talk to the people working with the robots, and they can give you some feedback on oh, I expected it to work this way, or maybe some insight that you would have missed yourself, but can help figure out what should be next steps, or maybe what was my model missing based on the responses I'm getting from users. So I do think there's inherent value to both.
Thanks.
Maybe I would actually, it reminds me, and this is just sort of free association a little bit, but yeah, it reminds me of just, straight up developing in simulation versus developing on the real world if you're a roboticist. So that, I think it's you have to keep yourself honest by trying your methods in the real world on occasion. But you're going to make a lot more progress and a lot faster, a lot faster discoveries if you also leverage simulation. And so, I would caution against doing either all the time. If you're just working on robots, you're going to be too slow. If you're just working in simulation, you're going to fool yourself. And so, you have to sort of establish for yourself a rhythm of every once in a while keeping yourself honest and validating in the real world. I think that goes for oracles and user studies too.
Thanks. So I think we can move to the next question with you all.
Yeah. So actually for the next question, since we talked a lot about rewards, so the next question is going to focus on that. So it's from Ellen Novoseller. And the question goes like this. Many algorithms in the interactive learning domain involve learning a reward function to explain human feedback. Do you feel that this is the most promising approach to learn the best policy from humans, or are there other alternatives? Are there ever limitations to assuming the existence of a reward function?
Yeah, so Michael Littman has some nice results on how not all reasonable preferences are expressible as a reward function, and he shows some nice examples where you can do more by having temporal logic statements or something like that. So I think it is definitely worth exploring other methods like that. But overall, I certainly think that inferring constraints or temporal logic statements or reward is definitely the path forward and is much more reasonable than doing behavioral cloning based methods for most types of tasks, just because it generalizes to the full space outside of where you've seen data much better and allows for improvement via RL. So I think that and reward functions are essentially just sort of the most compressed. They're essentially a compressed version of the value function or the optimal policy for a problem that gets decompressed by the transition dynamics of the environment. And so it is sort of the cleanest thing to try to infer that you can probably infer with the least data and also have the strongest priors for, in my opinion.
So I agree entirely with Scott when it comes to how do you learn from a demonstration. I completely agree. The question itself also asked about are there alternatives and limitations to this, and I think that's where you need other modalities. There's times when you don't have a demonstration, and there's other feedback modalities where inferring a reward function is not necessarily going to be the most necessarily the most efficient. Looking at, it is one way to do it. You can treat positive and negative feedback also as indications of a reward function, but it could be an advantage signal. It could be corrective feedback, things like that. But yeah, when it comes to learning from a demonstration, and if the alternative is behavioral cloning versus IRL, I agree with Scott entirely.
Okay. All right. Yeah, but I think that there is a trade-off here, because for instance, we could use, preferences or evaluative feedback in general is less demanding for the user, right? Than showing how to do something, or grabbing a robot and kinesthetic teach something, or to operate something. Is giving evaluations is less demanding from the user, but then we have the trade-off because we are talking about interactive robot learning, right? So then we cannot run several times a robot in the lab or learning something. And then these approaches that are less, the task load is lower, then it is because the information given probably is better, but is informationally poorer, right? Like if you compare to executions, you are saying this is better, but exactly you are not showing what is better. Then you need a lot of samples for that to get to know what is exactly the part that is making it better. But then this will require a lot of experience in the lab with the robot or whatever the robot is, whatever the robot is. So in interactive robot learning, we have this trade-off always to take into account.
Yeah, so
efficiency and user effort.
So I would love to hear your thoughts on that. That actually is a great segue to the next question that I have. So one of the things that we motivate learning from demonstration work in general is papers claim how it is easy for people to teach robots, right? That they don't need a lot of robotics experience. I mean, I myself included is guilty of claiming such things. And only we know, even if you think about kinesthetic demonstrations, while we claim it's easy, it is extremely difficult, even if it's a single manipulator, to hold the robot and do certain things. But at the same time, as Carlos was talking about, there's this trade-off about different modalities being useful in different contexts and different tasks. What are your thoughts on us as a robotics community having some sort of a consensus on, or a more systematic understanding of what modalities work better when, right? So is it that a person, let's say, starting to do research for the first time in this field needs to decide on a modality? Are there lessons that we have learned that can help them systematically make that choice? Or does it have to, again, be tested out for that particular test case?
So I think I can give an answer that ties some of a lot of these together. So, I think you don't really want to put that on people. I think, it has to be on the robot to know when to ask for, what kinds of feedback. And even within a certain modality of feedback, being active and, asking for the most informative types of things. To answer, part of Carlos's question, I think, about not really knowing, what was wrong in a demonstration. I think there are a lot of ways of kind of looking at that. Just active, asking, actively for certain types of preferences certainly helps to, narrow that down quickly, but it's still only, sort of one bit of information, and it doesn't help narrow it down super fast. So we have been trying to explore ways of having people, sort of say what they thought was wrong, either in natural language or showing a particular piece of a trajectory, or one really low sort of effort feedback thing that you can do is just sort of mark change points in a trajectory between where you think it's behaving near optimally and suboptimally. And then with very few sort of points you stick in there, you get a really dense labeling over what's good and bad in a trajectory without someone sort of having to go through and label tons and tons and tons of state action pairs. Or even another thing we've been using is like human gaze, and at least trying to get a notion of what features people are paying attention to, which, gives us a hint as to, what's connected to either what's going well or poorly, or even if someone's controlling something and giving demonstrations themselves, there are even certain eye gaze patterns actually that seem to correspond to if the task part is sort of more difficult or not, or if someone's unsure about what's going on. So there are a lot of sources of information that we can use, I think, to try to get better information there. But yeah, as you said, I think there's sort of always trade-offs between these different types of feedback, but the robot needs to have models of when those are going to be most useful and how informative they're going to be, so it can make the decisions itself, I think.
Yeah, if I could build on that, we've been thinking a lot about, sort of like Scott said, the order in which you could get different types of information. Like imagine you have a robot that you're trying to teach. You can show it demonstrations, of course, where the robot sort of waits and you show it the motion, maybe kinesthetically. The robot could ask you questions. It could show you example motions, and you could say, oh, that one was good, that one was bad. Or like Scott said, you could segment out parts that are good and bad. There's also, like, you could physically correct it. Like it could start doing a trajectory and you could grab it, slightly move it to somewhere else where it should be going. So there's like a lot, and I'm missing others, of course, as well. But these are just some examples of different types of corrections or ways you can provide information. And we've been thinking about, like, what's the right order? Like if we're going to combine multiple different types of these sources of information, like what's the order that we should use or robots should use to learn as much as possible, as quickly as possible? And at least so far, maybe focusing on the ones I've mentioned, what we found is that it's best to start off with a demonstration where the human shows the robot sort of the entire motion or some approximation of that entire motion. Maybe they get parts of it wrong. And then the robot comes back with questions where it's like, okay, I kind of understood this aspect. Like my belief over the reward function is very sure here. But there are other aspects where I'm like very confused. And that's where I should be asking like questions to elicit information, etc. So the order sort of naturally progresses between these, let's say, passive demonstrations where the robot waits and you show it something, and then this more active interaction where the robot's sort of querying you, hey, what about this? What about that other thing? And then between these two are these physical corrections where you can, as the robot's trying to show you these questions or trying to show you examples, you can make these slight changes. So that's kind of the hierarchy that we've seen that works best for eliciting information from users. But I think what I'm missing so far is, I haven't mentioned natural language, which I think also has a really important part to play here. And I'd be excited to hear other people's thoughts on where that might go or how we can use that more.
So maybe we can move to the next question. I have a question that is a bit more relaxed. So it's more in the side of the applications. So what kind of problems can be solved with interactive learning methods that cannot be solved with other imitation learning approaches? So it could be, maybe I would ask like to all the speakers to mention either in their experience or what you think potentially could be done that beforehand you think that interactive, having a human in the loop teaching an agent is definitely going to work in a problem that otherwise is not possible.
Okay, I'll take a swing. So I guess my feeling is that we need interactive learning for almost any real problem. I think that problems that are simple and done in the lab you can kind of get away without it because they're designed to be simple and there isn't a ton of ambiguity about what's being shown. And, there's a white background or a green background and, a single object and you're doing like pick and place or something. As soon as you introduce significant ambiguity, unless there's a lot of prior knowledge being brought in, which as we talked about earlier today, we don't really know how to do effectively yet. There almost certainly has to be a back and forth to ensure that there's not going to be reward hacking or misunderstanding in learning. So my view is that it's just absolutely critical for almost any deployed scenario that we can reasonably think of.
Especially when we recognize that different users might want to do the same task in very different ways, or like personalization is important. For me, that comes to mind because I'm thinking of assistive and rehabilitation robotics. But anytime where like the user has something that's very different from one person to another, of course, any like one size fits all algorithm is doomed to fail. And we want to interact with those users to figure out exactly what they need or what works best for them. Perhaps even when we're learning from users, different users have different teaching styles. And so that's another way which we can adapt to work with different people. So yeah, for me, I think of like often personalization is one of those things where I'm like, yeah, we definitely need to have this interactive learning if we want to be able to personalize.
And I think that's a great perspective is like, the to get robots into people's homes, you don't want them, and Leslie Cabling is always fond of saying, you don't want it learning in your kitchen, right? You want it to learn as much as it can in the factory, and then come to your house and learn with as little interaction as possible, how to personalize to your environment and your preferences. And I think that's the right perspective for us to take. Is that there's the space of getting good base behavior, which is one problem, and then there's the space of getting personalized, fine-tuned behavior with as little interaction as possible. That's a separate problem, and I think that's what this, in some sense, that's what this workshop was framed as, is focusing on that part.
Maybe one more viewpoint why I think the interactive learning is important is for the users to trust their robots. So in order for you, if you want to take a robot to your home, you want to know the robot will do what you want it to do. So actually the teaching process is something which allows you to gain some of the trust. So that by you see that the robot adapting to your own preferences, you're first better understanding, or you're getting more transparent behavior, what the robot really does and what it can do probably, as well as you're through that process of teaching, you're gaining more trust on its actions. So it'll do what you taught it to do, and not just some sort of behavior where you probably don't want the robot to run amok in your kitchen just by, okay, yes, it's been programmed in the factory to be able to do dishes.
Actually, there's another question in our list that I think is very related to this, and I'm actually really interested to know what your opinion is on this, which is basically about safety, right? So I mean, of course, safety is a concern for any type of learning approach, right? But I'm wondering if what do you think about safety in interactive learning, like both for the human and for the robot? Because I mean, the way I see it, you can perfectly have the robot misinterpreting a feedback and doing something that it's either bad for the robot itself or for the human, right? Do you have any particular insight on this?
Yes, I mean, I think this is the primary question that I think about is, especially in the imitation learning setting where you don't know the person's reward function. They have implicitly, in their head, how do you provide guarantees that the robot's going to behave reasonably? So, I mean, it's already a hard problem to do high confidence policy evaluation where you know a reward function and you just want to evaluate a policy with respect to it. That's already difficult to do efficiently, especially in off-policy settings. It's way harder, though, when you have the double uncertainty of not knowing how well any particular policy will perform with respect to a particular reward function and having large uncertainty, or any uncertainty at all, really, over what the reward function could be, given the demonstrations. And so, I mean, obviously the key is, as I and Anka and others were talking about, is keeping track of this uncertainty. But this is really challenging to do in a, computationally tractable way. And it's really hard to do in these super high dimensional problems where your inputs are these, unhelpful state variables like pixels. And you're really trying to build up to features where you're going to reasonably be able to assess risk in some reasonable space. And once again, coming back to the refrain, which feels a little bit like throwing up our hands up in the air, but saying that we need to bring in knowledge from other tasks, we need transfer learning, we need priors, and yet we want all these things to be, all those parts, including the priors, to be as data driven as possible, so that we're not leading ourselves astray. But yeah, I think right now the state of the art, especially in imitation learning, aside from like some of the work the my group's done and maybe a few other people, has really been pick your favorite algorithm, throw some data at it, and hope it works. And as much progress has been made in imitation learning, nobody is going to want to use algorithms like that. And so I think until the majority of imitation learning research moves over to a more sort of risk-sensitive paradigm, the field's not going to make much progress in terms of algorithms that are actually deployable or of interest to industry or end users.
I'll just point out again, that's sort of the maybe complementary perspective, is that's sort of the point of Apple-D and the work that we talked about in our talk, is that if you constrain what can be learned by having a structured stack of parameterized space, such that anywhere in that space is safe, and all you can do is learn to twiddle within those parameters. That's another way to go, is to and so the ROS navigation stacks have their own sort of safety mechanisms, and we're just trying to tune those parameters. That's another take on how to ensure safety. But yes, one way or another, for it to be needs to be adopted, we need to have some assurances.
Yeah. So actually, one thing I'll just interject there is, like, safety gets used in a lot of different ways, and I the kind of safety that Peter's talking about is, like, I think the standard usage of the word of, like, safety, where you don't want to destroy things, you don't want to break the robot, etc. Whenever I talk about it, like, I'm usually also talking about correctness. So, like, even that example of, like, no one's going to want to use a robot if they're not confident it's going to do what they actually showed it to do. We want robots not only that are going to damage things, but that are going to behave correctly. And that's not something I don't think that can be, dealt with by saying, well, we're only going to provide a class of policies that do correct things, because then we'd already be done. And so I think that part of it does require reasoning about uncertainty.
I think one other fun aspect of safety is that there are like multiple perspectives. So the robot, of course, its first job is to make sure that it is safe. It's not going to hit things, etc. But then its second job is actually to convince the humans around it that it's safe. Like imagine a self-driving car. Sure, like this car might know not to hit everything, might be like whatever. Like it might know that it's safe. But if I'm driving next to it and I see it moving erratically, or like I don't see it using its turn signal, like I am not convinced that this robot is safe. So we want to make sure that these robots are also, like we mentioned earlier, trust, intuitive, etc. I think all these also kind of relate to this bigger idea of making sure that we can have robots in our homes, our roads, etc., that are safe and also convince us that they're safe.
I think, of course, the safety is a very important issue, right? Also, of course, the one thing is, of course, physical, safety, harming the human and robot. And then, of course, there are a lot of works in the control community we could put it in order to ensure a lot of safety criteria there. But also one thing I think completely we have not worked on so much is how to ensure this kind of control point of the safety is embedded or guaranteed in our learned control policy. I think there is a lot of work should be done.
All right, awesome. So, Guli, if you have a thought, please finish it.
Yeah, maybe I can give one more viewpoint on safety. Thinking more from the RL point of view, and there's now quite a lot of works on safety, which basically, typically for safety, there is, for RL, one approach to look at it is that if there is some safe set in some state space that can be, or maybe some infer state space, so that basically the safety, whatever is the safety function, that safety function is a known function, even if the dynamics would be unknown, and even if the reward might be unknown, but the safety set is kind of pre-programmed and unknown, and whatever differentiable maybe even, and if you have that kind of notion of safety where you can directly from your observation space or state space define the safety, then of course we can go to much stronger guarantees, even under let's say stochastic, or at least stochastic guarantees on the safety. So these safe MPC like or safe RL type works have been, there's a lot of recent works in that area. We are also working on some of those in order to kind of provide stochastic guarantees of safety for those easier cases. Of course, when we have like what Scott is talking about, safety in terms of from pixel, we cannot define such safety constraints or safety functions for let's say images, for example, or anything like that. But I think that's another way of looking at the safety for kind of slightly more model-based settings. But the models in those settings may still learn models, as long as we have the notion of uncertain that's been coming up all the time in this discussion.
All right, thank you. So since we are pretty much out of time, the final question we have is if the panelists could take a second to mention what would be their one favorite open problem or the challenge for the field at large. I recognize you might have already alluded to this in some of the discussions we had before. We would love to know what would be if you had to choose, what would be your one favorite problem, open problem for the field?
All right, I can go first. Well, I'm working on imitation from observation. I think this is a key problem. Learning from being able to learn from non-expert video demonstrations without access to the actions, and then one that came up in our in the discussion today, which I think is a fantastic grand challenge, is being able to unify all of these different learning algorithms and approaches and modalities into as Scott said, putting it on the robot to know what algorithm it should use, what modality it should use, what advice it should ask for, and having this sort of grand unified theory of learning from interaction as opposed to lots of point solutions. That's, I think, something that would be great to maybe it's premature to go there right now, but at some point we need to go there.
I think mine would be asking the question of how we build models that allow us to compute a lot of these safety guarantees more efficiently, and that are necessarily abstracted and inaccurate models, but in the right way for still being able to provide true probabilistic safety guarantees. So ones that abstract away the right things that are not necessary for reasoning about safety. And this seems to be related to causal feature discovery and things like this. And I don't think anyone quite knows how to do this, and especially like in the safety space. A lot of people have largely shied away from models unless they're models that are perfect and handed to you, like sort of in the formal verification community, and in the sort of probabilistic type safety stuff. There's a pretty limited number of ways of using models. I mean, we've done some work with like using a model as a control variant so that you can reduce variance of estimators without, adding bias and things like that. But I think we need more meaningful ways of using models directly by abstracting away the right quantities that aren't going to affect our estimates, much like how humans just, consider a couple main factors of if I change, things in this way, what's it going to do? And I just don't think we have any idea how to do that.
So for me, there are multiple, of course, open questions I am now interested in. So maybe one thing would be can we also learn that somehow this symbolic reasoning from the human demonstrations, like what kind of things are really need to be done, and so on, like a lot of this connecting with the symbolic reasoning, context understanding, precondition and post-condition. These kind of thing would be very interesting for me, and understanding kind of different level of intention of the task, like very much high level purpose to the very low level motion or force and such levels. I think this unifying framework to learn this kind of complex task, would be, I think that is one of the interesting topic I am hoping to go towards too.
Yeah, mine is kind of building on that, but very general. I feel like the open challenge for me is just understanding the humans we're working with, or developing good models of those humans. Because if I want to learn from humans, I need to be able to explain their actions. Why did they take that action? Like, what should I learn from that? What's the meaning behind that action? Or conversely, what actions should I take to communicate with you? Like, what robot actions would convince you that I'm trustworthy or intelligent, or I've learned correctly, etc. So this like bidirectional communication between the human and robot, like, we know what the robot's doing, but it's really like the human's kind of a black box. Like, we have some models. I'm excited about developing better models and understanding this sort of interaction between the human and robot in a more rich sense. So I can really like take information away from the human and provide information to the human. Know that open problem isn't anything new. Like, this is certainly something we've been thinking about for quite a while. So I do think it's a worthwhile one.
Okay, my take on the question, I think that one of the challenges, really great challenges, has been around for, almost since the beginning, is the kind of the lack of hierarchy in skills. We're working always either on a very high-level abstraction on doing just sequencing of some primitives, or we're learning those individual primitives. We really don't have, or when we do end-to-end models, we really cannot capture sub-skills or primitives in those models often effectively, or we cannot at the same time learn both primitives as well as be able to abstract those to higher level compositional primitives that could be then composed into new skills. And I think that is still something that, whether it would be something that would go at all close to logic or anything like that, or whether it's just something that can be incorporated in the structure of the network or whatever else, we don't even know what's the substrate for that kind of compositional skills. And I think that in those cases, we get really interesting viewpoints because, for example, for learning, sub-skills. For example, if you have human demonstration, when we're talking about learning from demonstration, human, when they teach another person, they usually verbalize what they're teaching. And that verbalization, for example, tells often a lot about the structure of the skill. So we have actually feedback already about through the audio signals and through the natural language. We have knowledge about the structure that's almost never used. And it could be informative, and that would allow us to build understand the compositional structure, which would, I guess, be the way to get much more general skills and more reusable skills.
All right. Carlos, do you want to say a few things?
No, I would like to ask the other participants that are connected still, if you want to say something or ask any other questions before we wrap up. Also the other organizers that are connected, all the other authors. Please, Jens.
So to continue with that question, for me, I mean, it's kind of similar to the big question that we always had in imitation learning. So how much should we actually imitate a person, and what does it make a difference in terms of embodiment and these kind of things? But for this interactive learning, I think it gets even worse, because now we suddenly also have to decide when we actually stop learning from the human expert and when the robot decides that it should get creative on its own or start going its own path. So it's one of the other big open questions, I find.
Good. So if no one else have any other comments, like for complementing this question of the open challenges, so maybe we can wrap up here. It has been a very interesting discussion with all of you. Thanks the speakers for their contribution, the time for recording your talks, and also for being here today. Also to the authors of the contributions, papers that we got for this workshop. It was very interesting also to watch these presentations and discuss them earlier. We have talked about many things here, about applications of interactive learning, but also the problems that we have, concerns, different modalities that we have, ways of interaction, and we still will keep having many more doubts in the future. That's why we have a job now. Apart of that, just like really thank all of you, also the other organizers for helping us to run this event. It would have been even nicer if we could join together in Paris, but I think we also have to learn to do this online, because online events are the future, I think. Even after pandemic, there are many reasons for following that. I know that there are institutions already that are encouraging researchers to not travel so much, at least with airplanes. So, like, being more careful with selecting what conference to join. So if this keeps happening, so I think we will move on to online conferences, and we need to learn to do this, right? And I think we are experimenting with this. We've decided to run this workshop in a bit different way, as like just try to use the entire day for the normal presentations, but we wanted to like emphasize or give priority to these discussions, which are the more useful and joyful moment of the workshop. And I think we built with these discussions, and we learn, and we get different perspective of other researchers. And it's also nice to have a bit of controversy for also like adding noise to our exploration in our research. So yeah, thanks very much for the participation. If you want to say something else, the speakers or the other organizers, please feel free.
So I would like to thank very much the organizers, and then especially you made this workshop on the interactive robot learning. workshop was a very interactive discussion as well. So I think this was a key thing. So thank you very much.
Yeah, I also would like to second that and thank the organizers very much.
Yep, it was great. Thanks, everybody. I need to run as well, but so long.
Thank you, everyone. We really appreciate it. Take care. Okay, I think I'm just going to end the stream.